There is a point where size stops feeling large and starts feeling unreal. For most of human experience, scale has been manageable. We understand distance by walking it. We understand weight by lifting it. Even the size of Earth, vast as it is, still fits within something the mind can grasp. Mountains have edges. Oceans have horizons. The sky feels far, but not unreachable. The universe does not behave this way. As distance increases, understanding quietly thins out. Numbers grow faster than intuition. 1,000,000 and 1,000,000,000 stop feeling different. 1,000,000,000,000 becomes a word rather than a quantity. Somewhere along the way, scale stops being something we can imagine and becomes something we can only describe indirectly. This documentary is about that threshold. It is not about speed or violence or cosmic spectacle. It is about scale that accumulates slowly, silently, over immense stretches of time. It is about objects that do not announce themselves, yet shape everything around them simply by existing. If you enjoy long-form, calm science documentaries like this one, you're welcome to like the video or subscribe to the channel. It helps support future explorations into space, scale, and the quiet structure of the universe. And now, with that sense of scale in mind, we can begin. TON 618. Somewhere far beyond our galaxy, at a distance so great that light itself takes billions of years to reach us, there exists an object whose size challenges the limits of meaning. It does not shine. It does not erupt. It does not move across space in any dramatic way. Its presence is known only through how strongly it bends the universe around it. This object is called TON 618. TON 618 is a supermassive black hole, one of the most massive ever observed. Its mass is estimated to be tens of billions of times greater than that of our Sun. These numbers are often repeated, but rarely understood. They are too large to picture directly, too far removed from experience to feel real. And yet, they describe something that exists right now, quietly, at the edge of the observable universe. Unlike the black holes often imagined in popular culture, TON 618 is not an engine of destruction sweeping through space. It is distant, stable, ancient. It has likely existed in a similar state for billions of years, growing slowly, shaping its surroundings through gravity that operates without urgency or sound. What makes TON 618 difficult to understand is not what it does, but how large it is without needing to do anything at all. Its event horizon, the boundary beyond which light cannot escape, is so vast that familiar comparisons begin to collapse. The solar system no longer helps. Galaxies themselves become awkward reference points. At this scale, even comparison starts to fail, leaving only abstract descriptions and quiet acceptance. To understand TON 618, we cannot rush. We must build scale patiently, allowing intuition to stretch and eventually let go. This is not a journey toward danger or drama, but toward stillness, toward an object so large that it exists almost outside narrative, influencing space and time simply by remaining where it is. This is where the exploration truly begins. When size stops being intuitive. Human understanding of size is built from experience. We learn distance by moving through it. We learn scale by comparing one object to another, one space to the next. A room feels larger than a person. A city feels larger than a room. An ocean feels larger than a city. Each step outward still allows the mind to anchor itself to something familiar. Even when the numbers grow, they remain connected to sensation. This method works well on Earth. It even works to some extent within the solar system. The distance to the moon can be imagined as a long journey. The distance to the sun can be framed as light taking several minutes to arrive. Planets become dots, but their orbits can still be sketched, still placed in relation to one another. The mind stretches, but it does not break. The problem begins when scale increases faster than intuition can adapt. Large numbers do not behave the way small ones do. They do not accumulate meaning gradually. Instead, they pass a threshold where comparison stops adding clarity. 1,000 feels larger than 100. 1,000,000 feels meaningfully larger than 1,000. But 1,000,000,000 does not feel 1,000 times larger than 1,000,000. It feels like a different category altogether. At that point, numbers stop enhancing understanding and begin replacing it. This is not a flaw in human thinking. It is a boundary condition. Our brains evolved to track movement, threat, distance, and resources within a narrow range of scales. There was no evolutionary pressure to understand light years, stellar masses, or the curvature of space. Those concepts lie far outside the environment that shaped perception. In everyday life, scale is reinforced visually. Large objects dominate attention. Small objects recede. Movement signals importance. Stillness suggests irrelevance. In the universe, these assumptions fail quietly. Some of the most massive objects are invisible. Some of the most influential forces operate without motion. Size does not announce itself. It must be inferred. This is why the universe often feels counterintuitive rather than overwhelming. It does not confront the senses directly. It withdraws from them. Distance offers the first lesson. When astronomers speak of light years, they are not describing motion in the usual sense. They are describing time. Light, the fastest signal available, becomes the ruler by which distance is measured. Even this shortcut does not restore intuition. Saying that something is billions of light years away does not produce an image. It produces a pause. That pause is important. It is where understanding changes character. As distances grow, the universe stops feeling like a place and starts behaving like a structure. Objects are no longer encountered. They are positioned. Events do not happen nearby. They are inferred from patterns and delays. The universe becomes something to be modeled rather than pictured. Size behaves the same way. On Earth, large objects dominate smaller ones through contact. A mountain blocks movement. A building casts a shadow. In space, size expresses itself through gravity. Not as a force pulling things inward aggressively, but as a shaping influence. Gravity does not rush. It curves paths. It guides motion without urgency. This difference matters because it changes how large objects behave. Something can be unimaginably massive and yet entirely calm. It can remain unchanged for millions or billions of years. It can shape galaxies without ever touching them. This is the kind of scale we are approaching. Before that scale appears, it is important to understand why comparison eventually fails. Humans rely on metaphor to bridge gaps in understanding. We say something is the size of a city, or the mass of a mountain, or the distance between continents. These metaphors work because they compress unfamiliar quantities into known references. But metaphor has limits. At some point, every reference becomes too small to help. Saying that something is larger than the solar system sounds impressive, but it does not clarify. Saying it is larger than a galaxy begins to sound unreal. The reference itself dissolves. At that stage, scale becomes qualitative rather than quantitative. Objects are no longer described by size alone, but by the way they affect space, time, and structure. Understanding shifts from imagining to accepting. This transition is subtle. It does not happen with a single number. It happens gradually, as familiar anchors drop away. First, distance becomes abstract, then mass, then time. Eventually, scale stops being something the mind can hold all at once. The universe does not warn when this happens. It does not signal that a threshold has been crossed. It simply continues operating under the same physical laws, indifferent to whether those laws remain intuitive. Gravity is a useful guide here, because it does not scale emotionally. A small mass and a large mass follow the same equations. The difference lies only in magnitude. As mass increases, gravity does not change character. It becomes deeper, broader, more influential, but not more dramatic. This is why extremely massive objects are often associated with stillness rather than motion. Their influence is distributed across space. Their effects unfold slowly. They do not need to move quickly to matter. In human terms, this feels backward. We associate power with speed, volume, and visibility. In cosmic terms, power is often associated with patience, with duration, with the ability to remain unchanged while everything else responds. This is where scale begins to feel unfamiliar in a deeper sense, not just numerically, but philosophically. When objects become large enough, they no longer fit into stories built around action. They do not arrive. They do not depart. They persist. Their existence becomes a background condition rather than an event. They are not characters in the universe's narrative. They are part of its grammar. Understanding such objects requires a different kind of attention, one that is slower, one that does not expect resolution, one that is comfortable with the idea that significance does not always come with movement or change. This shift is essential for what follows. The object at the center of this documentary is not remarkable because it behaves unusually. It is remarkable because it pushes scale beyond the range where intuition remains useful. It reveals a region of understanding where numbers lose their grounding and meaning becomes distributed rather than focused. To approach it, we must resist the urge to visualize everything at once. We must allow understanding to be partial, and we must accept that some scales are not meant to be felt directly. In the universe, size does not always announce itself. Sometimes it waits quietly, influencing everything around it, while remaining almost impossible to picture. At those scales, comprehension is not a matter of clarity, but of patience. This is the threshold we are approaching. How size accumulates without urgency. When people imagine growth in the universe, they often picture sudden events, explosions, collisions, dramatic moments where something small becomes something large in a short span of time. These images are reinforced by the way space is often portrayed, full of violent births and catastrophic endings. While such events do occur, they are not the primary way size is built at the largest scales. The universe, most of the time, grows quietly. Large structures do not emerge because something happens quickly. They emerge because something happens continuously. Gravity, unlike most forces humans interact with, does not switch on and off. It does not require fuel. It does not become tired. It simply persists, accumulating influence as long as mass exists to sustain it. This persistence is what allows size to grow without urgency. A small amount of mass creates a small curvature in space. A larger amount creates a deeper one. But the relationship is smooth. There is no threshold where gravity suddenly becomes violent. As mass increases, space responds by bending more strongly, guiding the motion of nearby matter along gentler, longer paths. Over time, this guidance becomes structure. This is how the universe organizes itself. In regions where matter is slightly denser than average, gravity pulls more material inward, not rapidly, but steadily. As more mass gathers, the region becomes more influential, attracting even more matter. This process does not require collision in the everyday sense. It does not involve impact or destruction. It involves motion guided by curvature, unfolding over millions or billions of years. From a human perspective, this feels almost static. On cosmic timescales, however, it is constant activity. One of the most important consequences of this slow accumulation is stability. Structures built gradually tend to persist. They settle into configurations that minimize disruption, balancing inward pull with outward motion. Galaxies form rotating disks. Stars establish long-lived equilibrium states. Even black holes, often imagined as chaotic, are remarkably stable once formed. This stability is key to understanding how something can become enormous without becoming dramatic. Consider how matter moves near a massive object. It does not fall straight inward unless something removes its sideways motion. Instead, it curves. It orbits. It circles slowly, losing energy over time through subtle processes. The result is not collapse in a single moment, but gradual inward drift. At small scales, this motion is fast enough to notice. At large scales, it stretches out until it becomes almost imperceptible. Growth continues, but it does so quietly. This is why the universe's largest objects are often ancient. Their size is not the result of intensity, but of duration. They have had time, immense amounts of it, to accumulate mass through countless small interactions rather than a few large ones. Time, in this sense, is not just a backdrop. It is an active participant. When processes unfold slowly, they are less likely to disrupt what already exists. They allow systems to adjust continuously, redistributing energy and motion without breaking apart. This is why large-scale structures tend to be smooth rather than jagged, coherent rather than fragmented. Gravity favors patience. As mass accumulates, its influence spreads outward. The region of space affected by it grows larger, even if the object itself remains compact. This creates a situation where an object's presence is felt long before it is encountered. In fact, at extreme scales, direct encounter becomes irrelevant. Influence replaces contact. This is another way intuition begins to fail. On Earth, influence usually weakens quickly with distance. A sound fades, a force dissipates. In space, gravity diminishes with distance, but it never disappears entirely. For very massive objects, even a weak influence integrated over enormous distances becomes significant. Motion across entire galaxies can be shaped by something that is never directly seen. This leads to a subtle shift in how importance is distributed. At human scales, importance is often local. What is nearby matters most. At cosmic scales, importance becomes global. Objects matter not because they are encountered, but because they define the geometry through which everything else moves. This is why the largest objects in the universe are often invisible. They do not need to emit light to matter. Their significance lies in how they structure motion rather than how they appear. As we move toward understanding objects of extreme size, it becomes necessary to let go of certain expectations. We must stop expecting growth to look like change and stop expecting influence to look like action. At these scales, the most important processes are those that remain steady. The universe, at its largest scales, is conservative. It builds slowly. It changes reluctantly. It favors configurations that can endure. This endurance is what allows certain objects to reach sizes that seem unreasonable. not because the universe is reckless, but because it is consistent. Given enough time, even small advantages in mass accumulation compound. What begins as a slight imbalance becomes a dominant structure simply by persisting. There is a parallel here with geological processes on Earth. Mountains are not built by single events, but by sustained pressure over long periods. Continents drift not because of sudden motion, but because of constant, almost imperceptible movement. The end result appears dramatic only because the time scale is removed from everyday experience. In space, this effect is amplified. Distances are larger. Time scales are longer. The opportunity for accumulation is greater. Structures that might seem improbable become inevitable when given enough time and enough space. This inevitability is important. It suggests that extremely large objects are not anomalies in the universe, but natural outcomes. They represent what happens when gravity is allowed to operate without interruption over vast spans of time. This does not mean that every region of space produces such objects. Conditions still matter. Density, motion, and environment all influence outcomes. But where conditions are favorable, growth proceeds without haste and without spectacle. This understanding reframes how we think about extremes. Rather than being rare exceptions, they become endpoints along a continuum. The universe does not draw a sharp line between small and large. It allows size to scale smoothly, guided by the same principles at every level. As scale increases, however, the consequences of size become harder to interpret. At some point, the influence of an object extends so far that it begins to shape entire systems. Its presence becomes part of the background structure rather than a localized feature. This is where the story begins to approach its central subject. The object we will eventually focus on did not become enormous because of a single event or an unusual mechanism. It became enormous because it existed in a region where accumulation could continue for a very long time. Its size is a record of persistence rather than violence. Understanding this prepares us for what follows. It shifts attention away from questions of how something formed quickly and toward how something remained stable long enough to grow beyond intuitive limits. Gravity as geometry, not force. Gravity is often described as a pull. Something massive attracts something smaller, drawing it inward through empty space. This description works well enough for everyday use. It explains why objects fall, why planets orbit, and why stars hold together. But as scale increases, this picture begins to fail. The idea of gravity as a force pulling across distance becomes less helpful and eventually misleading. At the largest scales, gravity is better understood not as a pull, but as a shape. According to modern physics, mass does not reach outward to grab other objects. Instead, it changes the geometry of space and time around it. Space curves, time slows. Motion follows the contours of that curvature. Objects move not because they are being dragged, but because they are following the straightest possible paths through a curved structure. This distinction matters deeply when we talk about extreme mass. When gravity is framed as a force, it invites images of tension and strain. It suggests effort. When gravity is framed as geometry, it becomes passive. Space is curved, and objects move accordingly. Nothing needs to be exerted. Nothing needs to be sustained. The shape exists, and motion follows. This is why gravity scales so well. As mass increases, space curves more deeply. But the rules do not change. There is no new behavior introduced at large scales, no additional mechanism required. The same principle that causes a small object to orbit a star also governs the motion of entire galaxies. Only the depth and extent of the curvature differ. This continuity is essential for understanding how gravity builds giants. In regions where mass accumulates, space becomes slightly more curved than its surroundings. This difference, however small, guides motion over time. Matter drifts inward along these curves, not rapidly, but persistently. As more mass gathers, the curvature deepens, reinforcing the process. Nothing dramatic occurs at any single moment. Growth emerges from repetition rather than intensity. This is why gravity does not rush. If gravity behaved aggressively at large scales, the universe would be chaotic. Structures would collapse violently, tearing themselves apart before they could stabilize. Instead, gravity allows systems to settle into long-lived configurations. Orbits form. Rotations balance inward motion. Energy is redistributed gradually. This behavior is not accidental. It is a consequence of gravity's geometric nature. When an object moves through curved space-time, it is not being accelerated in the usual sense. It is following a path that appears curved only when viewed from a flat reference frame. Locally, the object feels no force at all. It is simply moving along the structure that exists. This perspective helps explain why extremely massive objects can remain calm. Their influence is spread across space rather than concentrated in a single interaction. They do not need to act. Their presence is enough. At smaller scales, this geometric view is often hidden by other forces. Electromagnetism dominates interactions between atoms. Pressure and friction shape motion in fluids and solids. Gravity becomes noticeable primarily when large masses are involved. As scale increases, gravity's quiet consistency begins to dominate. This is why gravity governs the largest structures in the universe. Galaxies form not because matter is violently pulled together, but because slight imbalances are amplified over time. Regions with slightly more mass curve space slightly more, guiding additional matter inward. Over billions of years, these regions become galaxies, clusters, and filaments. None of this requires urgency. The geometry of space does the work continuously, without pause. Motion follows curvature whether or not anything dramatic occurs. Growth proceeds whether or not it is observed. This also explains why gravity is difficult to shield against or interrupt. It is not a force transmitted through a medium. It is a property of the structure itself. As long as mass exists, curvature exists. As long as curvature exists, motion responds. At extreme scales, this creates environments where change is slow, but inexorable. Consider an object with immense mass. Its curvature extends far outward, influencing motion across vast distances. Objects within this region may orbit for millions of years, gradually losing energy through subtle processes. Over time, some of this matter drifts inward, adding to the mass that created the curvature in the first place. This feedback loop is gentle, but persistent. Nothing needs to fall directly inward. Nothing needs to collide head-on. Motion alone, guided by geometry, is sufficient. Over time, the result is accumulation. This is how gravity builds giants without violence. The idea of geometry also reframes how we think about stability. In a force-based view, stability seems fragile. Pull too hard, and systems collapse. In a geometric view, stability emerges naturally. Objects settle into paths that balance motion and curvature. Orbits are not precarious. They are preferred configurations. This preference for balance is why many massive systems endure for billions of years. Stars maintain equilibrium between gravity and pressure. Galaxies maintain equilibrium between gravitational attraction and rotational motion. Even black holes, once formed, represent a kind of equilibrium, an extreme one, but stable nonetheless. Understanding gravity as geometry also clarifies why extreme mass does not automatically imply chaos. As mass increases, curvature deepens, but motion remains smooth. Paths bend more strongly, but they do not break. The universe does not introduce turbulence simply because scale increases. This calmness is essential for what follows. The object at the center of this documentary exists in a regime where gravity dominates completely. Other forces become negligible by comparison. Electromagnetic interactions shape local behavior, but they do not determine structure. At that scale, geometry is everything. To prepare for that, it is necessary to release certain expectations. We must stop expecting gravity to look like force. We must stop expecting size to look like activity. Instead, we must become comfortable with the idea that the most massive objects are often the most still. This stillness is not absence. It is the presence of balance. As gravity builds mass over time, it also builds patience into the system. Rapid changes become less likely. Large systems resist sudden disruption. They respond slowly, adjusting over long periods rather than reacting sharply. This resistance to change is one reason extremely massive objects can survive for so long. They are not easily perturbed. Their geometry dominates local conditions so completely that external influences are smoothed out. At this point, gravity begins to feel less like a phenomenon and more like a context. It is not something that happens within the universe. It is something the universe is shaped by. This distinction matters when approaching black holes. Black holes are often framed as regions where gravity becomes infinite, where physics breaks down. While there are limits to current understanding, this framing exaggerates the drama. For most of a black hole's surroundings, gravity behaves exactly as expected. Space curves, motion follows. Nothing exceptional happens until extremely close to the center. From far away, even the largest black holes behave like ordinary massive objects. Their influence is measurable, predictable, and calm. The difference lies only in scale. This is why understanding gravity's geometric nature is essential before discussing extreme objects. It prevents misunderstanding. It removes unnecessary fear. It replaces imagery of violence with imagery of structure. When gravity begins to reshape time. As mass increases, gravity does more than guide motion through space. It begins to alter time itself. This idea can feel abstract at first, because time is usually experienced as uniform. Seconds pass at the same rate whether one is standing still or moving slowly. Days follow nights with dependable regularity. On Earth, differences in gravity are too small to produce noticeable changes in time. The effect exists, but it remains hidden beneath everyday experience. In the universe at large, time is not so rigid. According to relativity, time and space are not separate frameworks layered on top of reality. They are part of a single structure, space-time, shaped by mass and energy. When space curves, time curves with it. Where gravity is stronger, time moves more slowly, relative to regions where gravity is weaker. This slowing is not a mechanical delay, but a geometric consequence. At small scales, this effect is subtle. A clock on the surface of Earth runs slightly slower than a clock in orbit. The difference is tiny, but measurable. Satellites must correct for it to function accurately. Gravity, even here, is already shaping time. As mass increases, the effect grows. Near very massive objects, time slows more noticeably. Processes unfold more gradually when viewed from afar. Motion appears delayed. Change stretches out. This does not mean that anything feels different locally. For an object within that region, time still feels normal. The difference emerges only when comparisons are made across regions of differing curvature. This relativity of time becomes essential when approaching extreme mass. At large scales, gravity's influence extends outward, creating a gradient rather than a boundary. Time slows gradually as one moves closer to the mass. There is no sudden transition, no abrupt shift. The universe does not introduce discontinuities unless forced to do so. Instead, it prefers smooth change. This smoothness is why gravity can reshape time without causing disruption. As mass continues to accumulate, the curvature deepens. Paths through space bend more strongly. Time slows more significantly. The geometry becomes steeper, but still continuous. Objects orbit. Light follows curved paths. Signals take longer to escape. Everything responds, but nothing breaks. This behavior contrasts sharply with popular portrayals of black holes. They are often depicted as violent regions where physics collapses. In reality, most of the space surrounding a black hole behaves predictably. Time slows. Motion curves. The laws remain intact. Only at the very center do current theories lose clarity. This distinction is important because it reframes black holes not as exceptions, but as extensions. They represent the continuation of gravitational behavior into an extreme regime. Nothing fundamentally new is introduced until the limits of understanding are reached. Time dilation, in this context, is not a side effect. It is a feature. As gravity deepens, time becomes part of the structure that defines motion. Events that would occur quickly in flat space unfold more slowly near massive objects. Signals are delayed. Interactions stretch out. Change becomes less frequent. This slowing has consequences for growth. When time slows, processes near massive objects can persist longer relative to the outside universe. Matter orbiting a massive object experiences extended interaction with its environment. Energy is redistributed slowly. Motion becomes more stable. The system resists rapid change. This resistance further supports the quiet accumulation of mass. In extreme gravitational environments, matter does not rush inward. It circles. It adjusts. It loses energy gradually. Over time, some of it drifts closer, contributing to the mass that created the curvature in the first place. This process is slow, but it is relentless. Time dilation, then, becomes part of the feedback loop that allows very large objects to grow. The deeper the curvature, the more time stretches. The more time stretches, the more stable motion becomes. The more stable the motion, the longer accumulation can continue without disruption. This is not an explosive process, it is an architectural one. As gravity reshapes time, it also reshapes causality. Signals take longer to travel outward. Changes propagate slowly. From a distance, massive objects appear increasingly static. Their internal dynamics become difficult to observe, not because they are inactive, but because time itself is stretched around them. This creates the impression of stillness. At extreme scales, this stillness becomes one of the defining features. The most massive objects in the universe appear almost timeless. They change so slowly relative to their surroundings that they seem fixed. This does not mean they are frozen. It means they are operating on a different temporal scale. This concept is difficult to internalize because human experience is anchored to local time. We do not perceive time gradients directly. We infer them mathematically. We detect them through comparison. Without those tools, time feels absolute. Understanding extreme gravity requires letting go of that intuition. Near very massive objects, the distinction between space and time becomes increasingly blurred. Motion through space and progression through time are no longer independent. They become intertwined aspects of the same geometry. Paths through space-time curve in ways that affect both where something goes and when it arrives. This blending becomes especially important when discussing black holes. A black hole is not defined by destruction, but by boundary. The event horizon marks the region beyond which signals cannot escape to distant observers. This boundary is not a physical surface. It is a geometric feature of space-time itself. Approaching the event horizon, time dilation becomes extreme. From far away, motion appears to slow to a halt. Objects seem to freeze near the boundary, fading from view. This visual effect is not caused by physical stopping, but by the stretching of time. Locally, nothing special happens at the event horizon. Physics continues. Motion continues. Time continues normally for the object crossing it. The dramatic effects exist only in comparison. This reinforces an important theme. Gravity's most profound effects are relational. They emerge when perspectives differ. They are not experienced universally, but relative to position within the geometry. This relational nature complicates understanding, but it also reveals something fundamental. Extreme objects do not violate the rules of the universe. They reveal how those rules behave when pushed to their limits. As mass increases toward the extreme, gravity reshapes space, time, and motion into a tightly integrated structure. The universe becomes less intuitive, but more consistent. Nothing becomes chaotic. Instead, everything becomes deeply ordered. This order is what allows extreme objects to persist. Black holes, once formed, are among the most stable structures known. They do not evaporate quickly. They do not decay easily. They change slowly, governed by processes that operate over immense spans of time. This stability is a direct consequence of gravity's geometric nature. By reshaping time, gravity builds patience into the system. Rapid changes are suppressed. Accumulation proceeds quietly. Influence extends outward. The object becomes a fixed feature of its region of space-time. This prepares us for the next stage of the story: what black holes actually are. Black holes occupy a strange place in human imagination. They are often described as monsters of the universe, objects that devour everything nearby, tear matter apart, and represent the ultimate end of all structure. This imagery is powerful, but it is also misleading. It emphasizes drama over accuracy, motion over structure, fear over understanding. To understand objects like Ton 618, these assumptions must be set aside. A black hole is not defined by what it destroys. It is defined by how space and time are shaped around a region of extreme mass. Everything else follows from that. At its most basic level, a black hole forms when a large amount of mass becomes confined within a very small volume. When this happens, the curvature of space-time becomes so steep that there exists a boundary beyond which light itself cannot escape. This boundary is called the event horizon. It is not a surface in the physical sense. It is not solid. It does not exert force. It is simply a geometric limit, a line in space-time where outward paths cease to exist. Nothing special happens at this boundary locally. There is no wall, no shock, no sudden change in physical laws. The drama associated with the event horizon exists only from the perspective of distant observers. Up close, physics continues smoothly. This point alone overturns many popular ideas. Black holes do not act like cosmic vacuum cleaners. They do not pull objects in from afar with increasing urgency. From a distance, a black hole behaves exactly like any other object with the same mass. If the Sun were replaced by a black hole of equal mass, the planets would continue orbiting in nearly the same way. Gravity does not become stronger simply because an object is a black hole. It becomes different only very close to the center. This distinction is essential. Gravity depends on mass, not on the label we assign to an object. A black hole does not gain extra gravitational power by being a black hole. What makes it unusual is not the strength of its gravity at large distances, but the compactness of its mass. The same mass compressed into a smaller region produces stronger curvature nearby, but leaves distant space largely unchanged. This means that black holes are not inherently destructive on cosmic scales. They are not roaming threats. They are stable endpoints of gravitational collapse, quiet, persistent, and predictable. The confusion arises because black holes are associated with extreme environments. Near the center, tidal forces can become intense. Matter falling inward can be heated, stretched, and torn apart. But these effects occur only when something comes very close. They are not properties of the black hole's influence as a whole. In fact, most black holes spend the majority of their existence doing very little at all. Once formed, a black hole can persist for extraordinarily long periods. It does not need fuel. It does not burn. It does not decay rapidly. Its defining properties, mass, rotation, and charge, remain largely unchanged unless altered by interaction with its surroundings. In the absence of incoming matter, a black hole is almost perfectly quiet. This stillness is often overlooked. When astronomers detect black holes, they are usually not seeing the black hole itself. They are seeing matter around it. Gas heated by friction, light bent by gravity, stars orbiting unseen mass. The black hole remains dark. Its presence is inferred, not observed. This indirect nature contributes to misunderstanding. It encourages the idea that black holes are defined by activity, when in fact they are defined by absence. They do not emit light. They do not radiate energy in the usual sense. They are regions where certain paths through space-time no longer connect to the outside universe. To describe a black hole accurately, it helps to think in terms of boundaries rather than behavior. The event horizon marks a limit of communication. Beyond it, events cannot influence distant observers. This is not because signals are destroyed, but because space-time geometry no longer allows outward paths. Cause and effect continue locally, but they become disconnected from the broader universe. Inside this boundary, understanding becomes more difficult. Current theories predict a region of extreme curvature, often called a singularity, where known physics breaks down. This is not necessarily a physical point, but an indication that existing models are incomplete. What matters for our purposes is that this region is hidden. It cannot be observed directly. Its nature remains uncertain. Crucially, everything about this uncertainty is confined within the event horizon. Outside it, physics remains well behaved. Motion, time, and space behave predictably. The black hole does not infect its surroundings with instability. This containment is part of why black holes can exist without disrupting the universe. They are self-limiting structures. Their most extreme features are sealed away behind geometric boundaries. The rest of the universe interacts with them through gravity alone, which remains orderly and consistent. This is why black holes can coexist with galaxies. In fact, most large galaxies appear to host a supermassive black hole at their center. These black holes did not destroy their galaxies. On the contrary, they likely played a role in shaping them. Their gravitational influence helped organize surrounding matter, guiding the formation of stars and regulating the flow of gas over long timescales. This relationship is subtle. It does not involve constant feeding or violent interaction. It involves balance. As gas drifts toward a galactic center, some of it may eventually fall into the central black hole. But much of it settles into orbits, forms stars, or is redistributed through feedback processes. The black hole grows slowly. The galaxy evolves slowly. Neither overwhelms the other. This slow coevolution challenges the idea that black holes are inherently destructive. They are better understood as structural features of large systems, anchors of mass that influence organization rather than agents of chaos. Understanding this prepares us to think clearly about scale. When black holes are small, their influence is localized. When they are large, their influence extends farther, but remains calm. Size does not introduce instability. It introduces reach. This brings us closer to the kind of object we are ultimately concerned with. Supermassive black holes differ from stellar black holes not in kind, but in degree. They follow the same rules. They possess event horizons, curved space-time, and central regions beyond observation. The difference lies in mass and scale. As mass increases, the event horizon grows larger. Tidal forces at the horizon become gentler rather than stronger. Paradoxically, falling into a very large black hole can be less disruptive at the boundary than falling into a smaller one. The gradient of gravity becomes smoother as scale increases. This is another way intuition fails. We associate size with danger. In gravity, size often brings smoothness. Extreme mass spreads curvature over a wider region, reducing sharp changes. The environment becomes less violent at the boundary, even as it becomes more inescapable overall. This characteristic is essential for understanding the calm nature of extremely large black holes. They do not announce their presence through turbulence. They do not tear apart their surroundings indiscriminately. They shape space-time gently, guiding motion over vast distances without requiring direct interaction. At this point, the idea of a black hole begins to shift. It becomes less of an object and more of a region, less of an event and more of a condition. A black hole is not something that happens. It is something that exists. This framing allows us to approach the extreme without fear. When considering an object like TON 618, it is important to remember that it is not exceptional because it violates the rules. It is exceptional because it follows them to an extreme conclusion. It represents what gravity looks like when allowed to operate without interruption across immense spans of time. How black holes form without drama. The formation of a black hole is often imagined as a moment of collapse so violent that it tears the surrounding universe apart. This image comes from compressing an extraordinarily long process into a single mental picture. In reality, black holes do not arrive suddenly. They emerge as the final stage of gradual, predictable evolution. To understand how this happens, it is useful to step back from extremes and begin with balance. Most large objects in the universe exist in a state of equilibrium. Stars, for example, are held together by gravity pulling inward and pressure pushing outward. Nuclear reactions in their cores provide energy that counteracts gravitational collapse. As long as this balance holds, the star remains stable, changing only slowly over millions or billions of years. When that balance shifts, the story changes, but not abruptly. As a star exhausts its nuclear fuel, the outward pressure weakens. Gravity does not suddenly increase. It simply continues doing what it has always done. With less resistance, the star begins to contract. This contraction raises temperature and pressure in the core, sometimes triggering new reactions that temporarily restore balance. In massive stars, this sequence can repeat multiple times, producing heavier elements until no further energy-producing reactions are possible. At this point, gravity is no longer opposed. The collapse that follows is rapid by cosmic standards, but still governed by physical law rather than chaos. Matter falls inward. Density increases. Space-time curvature deepens. If the remaining mass is large enough and sufficiently compact, the collapse proceeds beyond any known stabilizing mechanism. An event horizon forms. A black hole is born. This description applies most directly to stellar black holes, which form from the remnants of massive stars. Their creation can involve energetic events such as supernovae, which are indeed dramatic. But the drama belongs to the star's death, not to the black hole itself. The black hole that remains is quiet. It inherits mass, not motion. Once formed, it settles into stability. This distinction matters because it prevents confusion between formation and existence. Supermassive black holes, like the one at the center of our own galaxy, follow a different path. They are not born from single stars. Instead, they grow over long periods through accumulation. Their origins likely involve early density fluctuations in the young universe, regions where matter was slightly more concentrated than average. These regions served as seeds, attracting surrounding material gradually. As galaxies formed around them, these central objects gained mass through slow inflow of gas, mergers with other black holes, and the continual guidance of matter along curved space-time paths. At no point did they require a single, catastrophic event to define them. Their growth was distributed across cosmic history. This distributed growth is essential for understanding extreme objects. When mass accumulates over billions of years, it does so under conditions that allow systems to adjust continuously. Angular momentum is redistributed. Energy is radiated away. Orbits settle. The process resembles sedimentation more than collapse. Layer upon layer added slowly, without disruption. In this context, the formation of a supermassive black hole is not an event, but a phase change. The object crosses a threshold where its mass becomes sufficiently compact that an event horizon exists. But nothing singular announces this transition. The universe does not mark the moment. From the outside, the object simply continues to influence its surroundings as it always has. This quiet transition is difficult to visualize because it lacks a dramatic marker. Yet it is precisely this absence of drama that allows black holes to coexist with their environments. They do not arrive as intruders. They grow alongside the systems they inhabit, shaping and being shaped in return. Galaxies evolve. Central black holes grow. The two processes remain coupled across cosmic time. This coupling has been observed indirectly. The mass of a galaxy's central black hole correlates strongly with properties of the galaxy itself, such as the velocity of stars in its core. This suggests coevolution rather than conflict. The black hole does not overpower the galaxy. It participates in its long-term structure. As black holes grow larger, their immediate surroundings become less extreme rather than more. Tidal forces near the event horizon decrease with increasing mass. The curvature of space-time is spread over a wider region. Gradients become smoother. Paradoxically, The boundary of a very large black hole can be gentler than that of a smaller one. This counterintuitive result further undermines the idea that black holes are defined by violence. At extreme scales, black holes become environments of patience. Matter approaching them has time to adjust. Orbits become wide and slow. Accretion disks, when present, extend across enormous distances, radiating energy gradually rather than explosively. Much of the time, even this activity is absent. A black hole does not need to be actively consuming matter to exist. It can remain isolated for long periods, interacting only through gravity. In such cases, it becomes almost impossible to detect directly. Its presence is revealed only through its influence on distant objects. This invisibility contributes to the impression that black holes are mysterious. In reality, they are simply extreme examples of a familiar process. Gravity acting without interruption. As scale increases, this process becomes harder to conceptualize, but not harder to describe. The equations governing black holes are well understood in their external regions. Predictions match observation. Orbits behave as expected. Light bends predictably. What becomes difficult is not the physics, but the imagination. At some point, mass becomes so large that reference points lose meaning. A black hole's event horizon may encompass regions larger than entire planetary systems. Its gravitational influence may extend across galaxies. Its growth history may span nearly the age of the universe itself. At this scale, formation is no longer a story with a beginning and end. It is a continuous narrative without a clear starting point. The black hole exists because conditions allowed it to grow, and because nothing interrupted that growth. This is the context in which objects like TON 618 must be understood. They are not anomalies produced by unlikely coincidences. They are the natural outcome of gravity given enough time, enough matter, and enough stability. Their size reflects persistence rather than exception. Understanding this helps dispel the urge to search for special explanations. There is no single moment when an object becomes extreme. There is only accumulation. This accumulation is not guaranteed everywhere. Many regions of the universe lack the density or stability required for such growth. But where conditions persist, growth continues. The universe does not impose an upper limit based on intuition. It allows size to increase as long as physical laws permit. This permissiveness is what leads to objects that challenge comprehension. As black holes grow larger, they also become more isolated in a conceptual sense. Their influence becomes so extended that local interactions blur into background structure. Their presence is felt everywhere nearby, yet their identity becomes diffuse. This diffusion of identity is important. It signals a transition from object to context. At extreme scales, a black hole is not just something within space-time. It becomes a dominant feature of the space-time region itself. This is the threshold we are approaching. From stellar to supermassive. Up to this point, black holes have been discussed as endpoints of familiar processes. Stars evolve, matter accumulates, gravity deepens. Within this framework, black holes are not interruptions, but continuations. Yet even within this continuity, scale introduces a quiet separation. There is a difference between a black hole formed from a single star and one that has grown for billions of years at the center of a galaxy. The difference is not in kind, but in context. Stellar black holes, formed from massive stars, carry masses several times that of the Sun. Their influence is strong nearby, but limited in reach. They are objects among many, participating in the motion of galaxies rather than defining it. Their presence is localized. Their identity remains clear. Supermassive black holes are something else entirely. They do not simply exist within galaxies. They occupy their centers. They are not passengers in cosmic motion. They are anchors. Around them, stars orbit, gas circulates, and entire galactic structures arrange themselves. Their influence is not confined to a neighborhood. It defines a core. This transition from stellar to supermassive does not occur abruptly. There is no dividing line where one category ends and the other begins. Instead, there is a continuum of mass, shaped by time, environment, and opportunity for growth. In the early universe, matter was more evenly distributed than it is today. Small variations in density were amplified by gravity over time. Regions with slightly more mass curved space slightly more, guiding surrounding material inward. As galaxies began to take shape, their centers became natural collection points. Motion slowed. Matter lingered longer. Accumulation became easier. In these central regions, black holes could grow in a way that stellar remnants could not. They were fed not by a single event, but by a steady environment. Gas flowed inward. Stars drifted closer. Mergers between galaxies brought additional mass and occasionally additional black holes. Each contribution was modest on its own. Together, across billions of years, they produced objects of immense mass. This slow growth is crucial to understanding why supermassive black holes are so large. Unlike stars, which must balance gravity against internal pressure, black holes have no internal structure to maintain. Once formed, they do not resist growth. They accept mass without needing to adjust. There is no threshold where added mass destabilizes the object. The geometry simply deepens. This makes supermassive black holes uniquely suited to accumulation. As they grow, their influence spreads outward. The region of space-time shaped by their mass expands. Orbits lengthen, motion slows, matter remains bound more easily. The environment becomes increasingly favorable for further growth. This feedback loop is gentle but powerful. Importantly, this growth does not require constant activity. Supermassive black holes often experience long periods of relative quiet, punctuated by episodes of increased inflow. Over cosmic time, even infrequent feeding is sufficient. Duration compensates for intensity. This is why supermassive black holes are ancient. Most formed early in the universe's history, when matter was more available and galaxies were assembling. Since then, they have persisted, growing slowly or remaining stable depending on their surroundings. Their mass reflects not a single era, but the cumulative effect of cosmic history. Understanding this timeline is essential for approaching extreme examples. When astronomers observe a supermassive black hole, they are not seeing a transient phenomenon. They are seeing the product of billions of years of gravitational consistency. The object's current state is not an accident. It is the result of uninterrupted opportunity. This perspective helps explain why the largest black holes tend to be found in the largest galaxies, particularly those at the centers of galaxy clusters. These environments provide the most stable conditions for long-term growth. Motion is slower. Interactions are frequent but gentle. Matter has time to settle. At these scales, the universe favors accumulation. As black holes grow larger, their defining features become less extreme locally. Tidal forces at the event horizon weaken. Space-time curvature spreads out. The boundary becomes smoother. The object becomes less violent at its edges, even as its total influence increases. This inversion of expectation is one of the most important ideas to carry forward. Larger black holes are not more chaotic. They are more patient. Their size dampens sharp gradients. Their influence becomes more uniform. They are not defined by turbulence, but by reach. This is why supermassive black holes can coexist with complex structures. They do not tear galaxies apart, they help organize them. Their presence stabilizes motion rather than disrupting it. As scale increases further, this organizing role becomes more pronounced. At some point, the mass of a black hole becomes so large that it challenges the usefulness of familiar reference frames. Galactic scales begin to feel small. Orbits span tens of thousands of light years. Time scales stretch beyond easy comprehension. This is where the narrative begins to approach its central figure. The largest known black holes are not merely larger versions of familiar objects. They occupy a regime where scale itself becomes difficult to describe. They sit at the upper edge of what is currently observed, not because they break rules, but because they test the limits of measurement. To move forward, it is important to hold on to one idea. Nothing about these objects is sudden. Their size is not the result of runaway processes. It is the outcome of persistence, when scale outgrows its categories. As supermassive black holes increase in mass, the language used to describe them begins to strain. Categories that once felt sufficient, stellar, intermediate, supermassive, start to lose their explanatory power. These labels are useful for organization, but they are not physical boundaries. Nature does not recognize them. Gravity does not adjust its behavior when a mass crosses a naming threshold. The universe continues smoothly. Human classification struggles to keep up. Astronomers rely on categories because they provide orientation. They allow patterns to be noticed and relationships to be studied. But as objects grow larger, categories become less descriptive and more symbolic. They signal scale without fully conveying it. This becomes evident when comparing supermassive black holes to one another. Some reside at the centers of modest galaxies, weighing millions of solar masses. Others sit within giant elliptical galaxies, reaching billions of solar masses. The difference between these extremes is not simply quantitative. It reshapes how surrounding space behaves, how stars move, and how time unfolds locally. Yet even here, the rules do not change. A black hole 10 times more massive than another does not introduce a new kind of gravity. It introduces more of the same geometry. Space curves more deeply. Time slows more noticeably. Orbits extend farther. Influence spreads wider. The process remains continuous. This continuity is what allows black holes to reach extraordinary sizes without destabilizing their environments. As mass grows, the region dominated by the black hole expands. Stars that once moved primarily under the influence of the surrounding galaxy begin to feel the central mass more strongly. Their orbits adjust. Their paths elongate. Over long periods, motion becomes more ordered around the core. This ordering effect is subtle. It does not force alignment. It nudges trajectories gently, shaping statistics rather than dictating behavior. Over millions of orbits, these nudges accumulate into structure. This is how extreme scale expresses itself, through long-term influence rather than immediate change. At some point, however, even these descriptions begin to feel inadequate. When a black hole's mass reaches tens of billions of times that of the Sun, the usual reference points begin to fail. Solar masses become meaningless units. Galactic centers become cramped metaphors. The object's influence extends across distances that challenge direct comparison. This is not a failure of measurement, but a limitation of language. Astronomers can estimate mass using orbital motion, light emission from surrounding matter, and the bending of light itself. These methods remain valid even at extreme scales. What changes is how the results are interpreted. Numbers can be produced, but intuition lags behind. When a black hole becomes extremely massive, its event horizon grows correspondingly large. Boundary expands outward, encompassing regions that would otherwise be associated with planetary systems or even star clusters. Yet locally, this boundary remains calm. Tidal forces near the horizon decrease as mass increases. The curvature is spread over a wider area. This leads to a paradoxical situation. The larger the black hole, the gentler its boundary. The point of no return becomes smoother, less disruptive. From the perspective of an object crossing it, the transition can be uneventful. The drama exists only in the scale of the outcome, not in the experience of the boundary itself. This inversion of expectation is a recurring theme. Human intuition associates size with intensity. In gravity, size often produces smoothness. Extreme mass dampens sharp gradients. It replaces abrupt change with extended influence. The universe trades violence for reach. As black holes grow larger, their internal timescales also stretch. Processes near the center unfold over longer periods when viewed from outside. Change becomes slower. Activity, when it occurs, is distributed across vast distances and times. This slow pace makes extreme objects difficult to study directly. They do not flicker. They do not vary rapidly. Their signals are subtle, requiring long observation and careful inference. Much of what is known comes from indirect evidence rather than direct imaging. This indirectness reinforces the sense that extreme black holes are elusive. In reality, they are simply operating on scales that do not align with human timeframes. As scale increases, the relationship between object and environment also changes. Smaller black holes exist within systems; they do not dominate. Supermassive black holes dominate their immediate surroundings. Extremely massive black holes begin to dominate regions so large that the distinction between object and environment becomes blurred. At this point, the black hole is no longer just something inside a galaxy. It becomes a defining feature of the galactic core itself. Motion, structure, and evolution in that region are inseparable from its presence. This blurring is important. It signals a transition from thinking of black holes as entities to thinking of them as conditions. At extreme scales, the black hole is not merely influencing space-time. It is shaping the context in which space-time dynamics occur. This shift challenges narrative thinking. Stories rely on boundaries. Characters act within settings. Events occur against backgrounds. Extreme objects dissolve these distinctions. They are not actors in a scene. They are the stage itself. Understanding this prepares us to approach the largest known black holes without distortion. When astronomers encounter objects whose mass exceeds previous expectations, they do not assume new physics immediately. Instead, they examine whether known processes, given enough time and opportunity, could produce such scale. In many cases, the answer is yes. This reinforces a central idea. The universe does not impose intuitive limits. It allows size to increase as long as conditions permit. What feels unreasonable to human perception may be entirely natural to gravity operating over billions of years. At the same time, extreme objects challenge observation. Distance compounds scale. The largest black holes tend to be found far away, in the early universe or in dense cosmic environments. Their light is red-shifted. Their signals are faint. Measurements carry uncertainty. Estimates vary. This uncertainty is not a weakness. It is a reflection of the difficulty inherent in studying objects that sit near the edge of observation. As mass increases, so does uncertainty, not because the object becomes ill-defined, but because measurement relies on indirect methods that become less precise at extreme distances and scales. Even so, patterns emerge. Some black holes stand out consistently, regardless of method. These are the objects that attract attention not for their drama, but for their persistence across data sets. At this stage, one particular object begins to emerge repeatedly. Its estimated mass remains extraordinarily high across multiple approaches. Its distance places it deep in cosmic history. Its influence is inferred through powerful, yet steady, emission from its surroundings. This object is not introduced suddenly. It is noticed gradually, as measurements accumulate and comparisons are made. Its significance lies not in novelty, but in extremity. It occupies the far end of the observed spectrum. It stretches the range of known masses. It challenges assumptions about growth rates and environments. It forces astronomers to revisit questions about how large a black hole can become without violating known physics. Importantly, it does not demand new laws. It demands patience. The object exists comfortably within general relativity. Its behavior is consistent with gravitational theory. What is uncomfortable is the scale itself. This discomfort is a signpost. It indicates that understanding is approaching a region where intuition fails, but consistency remains. Where numbers remain valid, but meaning becomes diffuse. Where description must slow down rather than accelerate. This is where the story begins to focus. Introducing TON 6118. By the time astronomers began to notice TON 6118, they were already familiar with large black holes. Supermassive black holes had been observed at the centers of many galaxies. Their masses, often millions or billions of times greater than that of the Sun, were no longer surprising. What made TON 6118 different was not that it belonged to a new category, but that it occupied the far edge of an existing one. It appeared not as an anomaly, but as an outlier. TON 6118 was not discovered through direct imaging. Like most black holes, it revealed itself indirectly, through light produced far beyond its event horizon. The object is associated with a distant quasar, a luminous region powered by matter moving in the intense gravitational environment around a black hole. The brightness of this quasar made it visible across enormous distances, allowing astronomers to study it even though the black hole itself remained unseen. This distance is significant. TON 6118 lies billions of light years away, meaning the light we observe today began its journey long before Earth existed in its current form. When we observe this system, we are not seeing it as it is now, but as it was deep in cosmic history. The universe was younger. Galaxies were still assembling. Conditions were different, yet gravity behaved in the same way it does today. This temporal separation adds to the challenge of understanding TON 6118. Distance and time blur together. The object exists far away in space and far back in time. Measurements must account for cosmic expansion, redshift, and the evolving structure of the universe. Even under these constraints, TON 6118 stands out. Its estimated mass is extraordinarily large. Using multiple methods, analyzing the motion of gas near the quasar, modeling the energy output of the surrounding accretion disk, and applying relationships between luminosity and mass, astronomers have arrived at estimates that place TON 618 at tens of billions of solar masses. While exact numbers vary, the order of magnitude remains consistent. This alone sets it apart. To place this in context, most supermassive black holes weigh between millions and a few billion solar masses. Objects exceeding 10 billion solar masses are rare. Objects exceeding 50 billion solar masses are exceptional. TON 618 occupies this extreme upper range. Yet even this description can mislead. Numbers of this size do not convey experience. They signal extremity without explaining it. To say that TON 618 is tens of billions of times more massive than the Sun is accurate. But it does not tell us how such mass manifests or why it matters. What makes TON 618 interesting is not just its mass, but how that mass interacts with space, time, and environment. The quasar associated with TON 618 emits enormous amounts of energy, not because the black hole itself shines, but because matter spiraling around it releases energy as it moves through intense gravitational gradients. This emission is steady rather than explosive. It reflects long-term accretion rather than sudden collapse. This steadiness suggests a system that has been stable for a long time. The environment around TON 618 must have supported sustained growth. Gas must have been available. Motion must have been organized. The geometry of space-time must have allowed matter to settle rather than disperse. These conditions are not trivial. They require a particular combination of density, stability, and duration. TON 618 is evidence that such conditions existed. Its presence implies that the early universe was capable of producing not just supermassive black holes, but extremely massive ones, given the right circumstances. This challenges simple narratives about growth limits. It suggests that the universe does not impose an obvious upper bound on black hole mass within the range of observed physics. At the same time, TON 618 does not appear to violate any known laws. Its inferred mass, while extreme, is consistent with general relativity. Its luminosity, while high, can be explained by accretion processes. Its stability aligns with expectations for objects of its size. What it challenges is not theory, but expectation. This distinction is subtle, but important. When something challenges theory, it demands new explanations. When it challenges expectation, it demands patience and refinement. TON 618 belongs to the latter category. It asks whether existing processes, extended across enough time and space, can produce outcomes that feel unreasonable to intuition. So far, the answer appears to be yes. Another aspect that sets TON 618 apart is its scale relative to its surroundings. The region influenced by its gravity is vast. The event horizon alone would encompass distances that dwarf familiar planetary systems. Beyond that, the gravitational influence extends outward, shaping the motion of matter across regions that would otherwise be considered galactic in scale. Yet this influence remains gentle. There is no evidence that TON 618 disrupts its environment violently. The quasar emission, while intense, does not imply instability. It reflects matter following curved paths, releasing energy gradually as it settles into deeper orbits. This process can continue for millions of years without exhausting available material. This longevity reinforces the theme of patience. TON 618 is not a transient phenomenon. It is not a momentary spike in activity. It is a long-lived structure that has persisted across a significant fraction of cosmic history. Its size is a record of sustained conditions rather than brief excess. This record is encoded not in images, but in influence. Astronomers infer TON 618's properties by observing how light behaves in its vicinity. Spectral lines broaden, emission intensifies, motion reveals mass. These clues are pieced together into a coherent picture, one that remains indirect but robust. This indirectness is worth emphasizing. TON 618 cannot be approached, imaged, or experienced directly. It exists at a distance that precludes intimacy. Understanding it requires acceptance of abstraction. We rely on models, correlations, and consistency rather than direct sensation. This reliance on inference is not a weakness. It is a testament to how far understanding can reach without direct contact. TON 618 is a reminder that much of the universe is known through absence rather than presence. We observe what surrounds it, what moves near it, what light emerges from its influence. The object itself remains dark. This darkness is not emptiness. It is concentration. Within the region defined by its event horizon, mass and curvature reach levels that disconnect that region from the rest of the universe. Information does not escape. Events do not propagate outward. The interior becomes a closed chapter in cosmic history. From the outside, this closure contributes to stillness. The most extreme processes associated with TON 618 are hidden. What remains visible is structure, motion that is orderly, emission that is steady, influence that is widespread but calm. This calmness is one of the most striking features of extreme black holes. Despite their mass, they do not dominate attention through activity. They dominate through context. They define regions of space-time that yet everything else must navigate. They do not need to act to matter. TON 618 exemplifies this principle at the highest observed scale. It is not unique in kind. Other extremely massive black holes exist, but it sits at the edge of the known distribution, where numbers become difficult to interpret and categories lose clarity. It marks a boundary not of physics, but of familiarity. This boundary invites reflection. Why does such an object exist? Not in the sense of purpose, but in the sense of possibility. What conditions allowed gravity to operate so effectively for so long without interruption? What does this say about the early universe and its capacity for structure? These questions do not demand immediate answers. They require slow consideration. TON 618 does not force a revision of understanding. It extends it. It suggests that the universe is comfortable producing objects that lie far beyond human scale, provided there is time and consistency. This comfort is humbling. As observers, we often search for limits. We ask how large, how massive, how extreme something can be before rules break. TON 618 suggests that the universe's limits may lie far beyond where intuition expects them. This does not mean there is no upper bound. It means that the bound, if it exists, has not yet been encountered. Measuring something too large to see. Understanding an object like TON 618 requires a shift in how certainty is defined. There is no image that captures its boundary. There is no probe that can approach it. There is no direct measurement of its mass in the way one might weigh a planet or track a star. Everything known about TON 618 comes from inference, careful, layered, and indirect. This is not unusual in astronomy. It is simply taken to an extreme. At great distances, even relatively simple objects become difficult to measure. When distance stretches into billions of light years, every observation carries uncertainty. Light weakens, signals blur, time intervenes. Yet despite this, patterns remain detectable. Motion still encodes mass, energy still follows predictable relationships. Gravity leaves traces that can be read, even when the source remains unseen. The challenge with TON 618 is not that it defies measurement, but that it sits at the upper edge of every method used to measure black holes. One of the primary ways astronomers estimate the mass of distant black holes is by studying the motion of gas in their vicinity. In active systems like quasars, gas near the black hole emits light as it heats up. This light carries information about how fast the gas is moving. Faster motion implies stronger gravity. Stronger gravity implies greater mass. In practice, this involves analyzing spectral lines, specific wavelengths of light emitted by atoms in the gas. These lines broaden when the gas moves rapidly. By measuring how much broadening occurs, astronomers can infer the velocity of the gas, and from that, estimate the mass of the central object. This method works remarkably well across a wide range of scales. However, at extreme distances, it becomes less precise. The light has traveled for billions of years, stretched by cosmic expansion. The environment around the black hole may differ from local examples. Assumptions must be made about geometry and orientation. Each assumption introduces uncertainty. Even so, when this method is applied to TN 618, the results consistently point toward extraordinary mass. Another approach relies on luminosity. There is a known relationship between the brightness of a quasar and the mass of the black hole powering it, particularly when the system is accreting matter efficiently. This relationship is not exact, but it provides a useful constraint. Extremely luminous quasars generally require extremely massive black holes to sustain their output without becoming unstable. TN 618's associated quasar is among the most luminous known. This luminosity does not fluctuate wildly. It appears steady over the timescales accessible to observation. Such steadiness suggests a massive, stable central engine rather than a smaller object undergoing brief bursts of activity. The mass required to support this level of emission, under known physical limits, aligns with the higher end of mass estimates. A third method involves gravitational influence on larger scales. In some cases, the motion of stars or gas clouds farther from the center can be used to estimate the total enclosed mass. For TN 618, this approach is more difficult due to distance and resolution limits. Individual stars cannot be resolved. Instead, broader patterns must be interpreted. Despite these limitations, independent lines of evidence converge. This convergence is important. No single measurement defines TN 618. Rather, it is the agreement among imperfect methods that gives confidence. Each approach carries uncertainty, but they point in the same direction. When multiple techniques produce similar results, even at extreme scales, the conclusion becomes difficult to dismiss. That conclusion is not a precise number. Astronomers do not claim to know the exact mass of TN 618. Estimates vary, often by billions of solar masses. This range reflects the limits of current observation rather than confusion. What matters is not the exact figure, but the scale it represents. TN 618 is not slightly larger than typical supermassive black holes. It is dramatically larger. This distinction persists even when conservative assumptions are used, even at the lower end of estimates. TN 618 remains among the most massive black holes ever identified. Its position at the extreme end of the distribution is robust against uncertainty. Uncertainty, in this context, becomes part of the story. As objects grow larger and more distant, measurement becomes less about precision and more about boundaries. We learn not exactly how massive something is, but how massive it must be at minimum. We learn that it exceeds known examples by a significant margin. We learn that it challenges expectations without breaking theory. This kind of knowledge is quieter than exact figures, but no less meaningful. It reflects a universe where extremes exist comfortably beyond human scale, accessible only through inference and patience. It also reflects the limits of observation, which are shaped not by lack of understanding, but by distance and time. TON 618 sits near the edge of what can be observed directly. Its light arrives stretched and faint. Its signals are filtered through cosmic history. The universe between it and us has expanded, evolved, and rearranged itself. Every measurement is a glimpse through layers of change. Yet even through these layers, TON 618 remains prominent. This persistence across observational methods suggests that the object is not an artifact of measurement or interpretation. It is not a statistical anomaly that disappears under scrutiny. It is a genuine feature of the universe, consistently revealed whenever data is examined carefully. This consistency matters because it grounds the discussion. It allows TON 618 to be treated not as speculation, but as a real, physical system governed by known laws. It shifts the conversation away from whether such an object exists and toward what its existence implies. One implication concerns growth rates. For TON 618 to reach its estimated mass by the time we observe it, growth must have occurred relatively efficiently in the early universe. This does not require exotic physics, but it does require favorable conditions, dense environments, sustained inflow of matter, and minimal disruption. These conditions likely existed in certain regions during the universe's early epochs. Galaxies were forming. Matter was more concentrated. Interactions were frequent. In such settings, black holes could grow rapidly without violating known limits. TON 618 appears to be a product of such an environment. Another implication concerns rarity. Objects like TON 618 are not common. They represent the extreme tail of a distribution. Most black holes are much smaller. Even among supermassive black holes, masses of this magnitude are unusual. This rarity is expected. Extreme outcomes require extreme circumstances sustained over long periods. Rarity, however, does not imply impossibility. In a universe as large and old as ours, even unlikely, combinations of conditions can occur. Given enough time and enough regions, gravity will occasionally produce outcomes that stretch intuition. TON 618 is one such outcome. This perspective helps avoid misinterpretation. It is tempting to treat TON 618 as a singular exception, a challenge to understanding. In reality, it is better viewed as a marker of scale. It shows what is possible when known processes are allowed to operate at their upper limits. This framing aligns with how science progresses. Rather than focusing on outliers as threats to theory, scientists examine them as opportunities to test boundaries. Extreme objects refine understanding by revealing where models remain valid and where assumptions need adjustment. TON 618 contributes to this refinement without overturning established physics. Another important aspect of measuring TON 618 is humility. Astronomers openly acknowledge uncertainty. They do not present estimates as absolute. They revise figures as new data becomes available. This openness is not weakness. It is an essential feature of working at the edge of observation. At these scales, certainty is incremental. Each new observation narrows ranges, strengthens correlations, or clarifies context. Over time, understanding deepens, even if exact numbers remain elusive. The picture becomes clearer, not through precision, but through consistency. TON 618 exemplifies this process. Its estimated mass has evolved as methods improve and data accumulates. Yet throughout these refinements, its status as an extreme object has remained unchanged. It continues to sit at or near the upper bound of observed black hole masses. This stability across revision reinforces confidence. It suggests that while details may shift, the central fact remains. The universe contains black holes of staggering size, far beyond everyday comprehension, existing calmly within the framework of known physics. This realization invites a shift in focus. Rather than asking how such an object can exist, it becomes more interesting to ask what it does to its surroundings. How does a black hole of this scale shape space, time, and structure across vast regions? How does its presence alter the behavior of matter and light on scales that challenge description? These questions move the discussion away from measurement and toward influence. They also move us closer to the heart of the story. When comparison begins to fail, human understanding relies on comparison. We understand something large by placing it next to something smaller. We understand distance by measuring how long it would take to cross. We understand mass by imagining weight. These strategies work well at familiar scales, and they work reasonably well at astronomical ones, up to a point. Beyond that point, comparison stops clarifying and begins obscuring. When astronomers describe the size of a black hole like TON 618, they often begin with familiar references. They compare its mass to that of the Sun. They describe how many solar systems could fit within its event horizon. They speak of orbits larger than galaxies. Each comparison is accurate, but none of them are sufficient. The problem is not exaggeration. The problem is that reference points collapse. To say that TON 618 is tens of billions of times more massive than the Sun does not evoke a meaningful picture. The Sun itself is already far outside everyday intuition. Multiplying that abstraction by billions does not extend understanding. It replaces it. At this scale, numbers stop functioning as tools for imagination. They become labels. The same is true for distance. The event horizon of TON 6118 would extend far beyond the scale of planetary systems. Yet planetary systems are already abstractions to most people. They are diagrams, not experiences. Enlarging them further does not increase clarity. It increases silence. This silence is not empty. It is the space where intuition no longer operates. Comparison fails because it assumes linearity, that understanding grows proportionally with size. The universe does not behave this way. Scale increases faster than meaning. Each step outward demands a greater leap of abstraction, until eventually there is nothing left to anchor to. At that point, scale becomes qualitative. TON 618 is not larger than familiar objects in a way that matters experientially. It occupies a different regime entirely. Its size does not invite comparison. It dissolves it. The object cannot be placed meaningfully alongside planets, stars, or even galaxies without distorting what those things are. This is why extreme scale often feels unreal rather than impressive. The mind searches for a frame and finds none. It searches for boundaries and finds only extension. It searches for motion and finds stillness. The object exists not as a thing among other things, but as a dominant feature of space itself. This shift is subtle but profound. At smaller scales, objects are contained within space. At extreme scales, objects begin to define space. Their gravity shapes the region so completely that everything else becomes secondary. Motion, structure, and time organize themselves around the mass rather than the mass fitting into an existing framework. This is what TON 618 represents. It is not merely a black hole with a very large number attached. It is a case where mass has become so concentrated and influence so extended that the usual hierarchy of objects breaks down. The black hole does not sit inside its environment. It is the environment's organizing principle. This is why visualization becomes misleading. Artists often depict black holes as compact objects surrounded by swirling disks. While this is technically accurate, it hides the most important aspect: scale. The disk is not a small ring. It can span distances comparable to entire galaxies. The motion within it unfolds over immense spans of time. At this scale, nothing appears fast, nothing appears violent. Everything appears stretched. TON 618 does not overwhelm through action. It overwhelms through persistence. This persistence is what challenges comparison most deeply. The object does not change quickly enough to provide narrative hooks. It does not erupt, collapse, or transform in ways that mark progress. It remains. And by remaining, it exerts influence continuously. Influence without events is difficult to conceptualize. Human stories rely on change, before and after, cause and effect. TON 618 resists this structure. Its story is not about what happens, but about what continues to be the case. This continuity is unsettling in a quiet way. The object has likely existed in roughly its current state for billions of years. During that time, galaxies have evolved. Stars have formed and died. The universe has expanded. Yet TON 618 has remained, altering little, accumulating slowly, shaping motion without interruption. At this scale, change becomes optional. This is where comparison not only fails, but becomes irrelevant. What matters is not how TON 618 compares to something else, but how it defines a region of reality that operates differently from familiar environments. Understanding this requires a shift away from imagery and toward acceptance. We must allow scale to remain abstract. We must resist the urge to compress it into metaphors. We must acknowledge that some objects cannot be understood by analogy, only by implication. TON 618 implies that the universe is comfortable producing structures that lie far beyond experiential meaning. It implies that gravity, given enough time, does not stop at convenience. It continues until constrained by physical law, not by intuition. This implication prepares us for the next step. Because if comparison fails, then what remains is not size, but effect. Not how large something is, but how it reshapes everything around it. Scale without reference points. When reference points disappear, understanding does not end. It changes direction. Instead of asking how large something is, we begin to ask what it does, how it structures motion, how it alters time, how it influences regions far beyond itself. At extreme scale, function replaces form as the primary way of knowing. TON 618 is known not through size alone, but through its effects. Its gravity shapes the motion of matter across enormous distances. Gas does not simply fall inward. It settles into extended orbits. It circulates slowly, guided by curvature rather than pulled by force. The region influenced by this motion is vast, and within it, behavior changes subtly but persistently. At this scale, gravity becomes a background condition. Objects moving within the influence of TON 618 do not experience it as a localized attraction. They experience it as the geometry of their environment. Paths curve, time stretches, stability emerges. Motion becomes ordered not because of boundaries, but because of dominance. This dominance is not aggressive. TON 618 does not impose itself through disruption. It does not eject matter indiscriminately. It does not tear apart its surroundings unless something ventures very close. Most of its influence is gentle, guiding rather than forcing. This gentleness is a direct consequence of scale. As mass increases, gravitational gradients smooth out. Differences become less sharp. Tidal forces near the event horizon decrease, rather than intensify. The space around the black hole becomes more uniform, not less. This inversion is difficult to accept intuitively. We expect larger things to be harsher. Gravity behaves oppositely. Larger black holes produce calmer boundaries. Their extreme nature is not expressed through violence, but through reach. This reach extends not only through space, but through time. Near an object as massive as Tan 618, time behaves differently. Processes unfold more slowly relative to distant observers. Signals are delayed. Change stretches out. From far away, the region appears almost frozen, not because nothing happens, but because time itself is curved. This temporal distortion reinforces stillness. The system appears stable because it is stable, not temporarily, but structurally. Large-scale motion settles into patterns that persist for immense durations. Disruption becomes rare. Adjustment becomes gradual. This stability is one reason objects like Tan 618 can exist at all. If extreme mass produced instability, such objects would be short-lived. They would tear themselves apart or disrupt their environments until conditions changed. Instead, gravity favors endurance. It builds systems that resist rapid change. Tan 618 represents the extreme expression of this tendency. It is not a dynamic object in the usual sense. It is a long-lived feature of cosmic structure. Its existence is less like an event and more like a geological formation, except that its scale is astronomical and its medium is space-time itself. This comparison, too, eventually fails. Geological formations exist within environments that change. Tectonic plates move. Erosion reshapes landscapes. Tan 618 exists within a universe that evolves. But its local dominance insulates it from many of those changes. It persists while contexts shift around it. This persistence challenges narrative thinking. There is no clear beginning to Tan 618's significance. There is no climax. There is no resolution. It simply continues to exist, influencing everything within reach and remaining unaffected by most of what occurs around it. This absence of narrative is precisely what makes it compelling for reflection. Tan 618 does not ask to be watched. It does not reward attention with spectacle. It exists whether observed or not. Its influence is not dependent on recognition. This quality aligns with a deeper truth about the universe. Most of reality does not exist for observation. It exists because physical laws allow it to exist. Structures persist because they are stable, not because they are interesting. Tan 618 exemplifies this principle at the highest observed scale. Its size does not carry meaning in itself. Meaning arises only when we attempt to relate to it. When we ask what it says about gravity, time, and the universe's capacity for structure. In this sense, Tan 618 is less an object and more a question. Not a question with an answer, but a question that reshapes perspective. It forces recognition of limits of intuition, limits of narrative, limits of comparison. And in doing so, it reveals something quiet and important. The universe is not arranged around human understanding. It does not pause at scales that feel reasonable. It continues smoothly and patiently, producing structures that lie far beyond what can be imagined directly. Tan 618 is one of those structures. It exists at a scale where size stops being descriptive and becomes contextual, where mass no longer invites metaphor, where gravity defines reality rather than interacting within it. This realization does not diminish understanding. It deepens it. It invites a slower kind of attention, one that does not seek to visualize everything, but accepts abstraction as a form of clarity, one that allows the universe to remain vast without demanding reduction. Gravity at its limit. When gravity reaches extreme scales, it does not become chaotic, it becomes dominant. At ordinary scales, gravity competes with other forces. Electromagnetism governs atoms and molecules. Pressure shapes fluids and atmospheres. Nuclear forces bind matter at its core. Gravity, though ever present, often feels secondary, subtle, slow, easily countered by structure and motion. Near an object like Ton 618, this balance disappears. Gravity does not merely influence motion, it defines it. Other forces still operate locally, but they do so within a framework entirely shaped by curvature. Space-time becomes the primary condition. Everything else adapts. This dominance does not arrive suddenly. There is no sharp boundary where gravity takes over. Instead, its influence deepens gradually as mass increases. Paths bend more strongly. Orbits widen. Time stretches. Motion becomes increasingly constrained by geometry rather than force. At this point, gravity stops feeling like interaction and starts feeling like environment. Objects moving within the influence of Ton 618 are not being pulled toward it in the intuitive sense. They are following the structure of space-time as it exists there. Their motion is not driven by attraction, but by necessity. The available paths simply lead inward, around, or along extended curves that wrap the region. This distinction is subtle, but essential. When gravity is treated as force, extreme mass suggests violence. When gravity is treated as geometry, extreme mass suggests inevitability. Things move as they must, not because they are compelled, but because alternatives do not exist. This inevitability is calm. Near Ton 618, matter does not rush inward. It settles. It circulates. It follows elongated orbits that can take thousands or millions of years to complete. Energy is released gradually as motion adjusts to deeper curvature. The system favors slow redistribution rather than sudden collapse. This behavior reflects gravity at its limit. At extreme mass, gravity becomes so pervasive that change slows. Motion smooths out. Instability is dampened. The system resists disruption not through rigidity, but through scale. Disturbances become insignificant compared to the total structure. This resistance is not perfect, but it is profound. Consider what it means for gravity to dominate a region thousands of light years across. Within that region, local variations matter less. Individual stars, clouds of gas, even entire star clusters become small perturbations within a vast curvature. Their interactions are secondary to the overarching geometry. This hierarchy of influence creates order. Motion becomes predictable at large scales. Patterns persist. Orbits remain stable. The region behaves more like a slowly rotating system than a collection of independent objects. Gravity's dominance produces coherence rather than chaos. This coherence is one reason extreme black holes can exist without tearing their surroundings apart. If gravity at extreme scales were violent, the environment would never settle. Matter would collapse too quickly. Energy would be released catastrophically. Growth would be self-limiting. Instead, gravity at its limit produces smooth, extended influence that allows systems to endure. Ton 618 exemplifies this endurance. Its gravitational field is immense, yet its surroundings are not in constant turmoil. The quasar emission associated with it reflects ordered motion, not disintegration. Matter follows stable paths. Energy release remains regulated by geometry rather than eruptive force. This stability is not accidental. As gravity deepens, the system's response becomes more uniform. Local differences average out. Sharp gradients soften. The region becomes less sensitive to disturbance. In this sense, extreme mass produces robustness. This robustness challenges everyday intuition. In human experience, large systems often feel fragile. Complexity introduces vulnerability. More parts mean more ways to fail. In gravity-dominated systems, the opposite can be true. Scale introduces simplicity. Influence becomes centralized. Variations become negligible. This inversion is central to understanding gravity at its limit. TON 6118 is not precariously balanced. It is deeply settled. Its mass anchors a region of space-time so thoroughly that change becomes slow by default. The system does not need to actively maintain stability. Stability emerges naturally from scale. This natural stability extends to motion near the event horizon. As discussed earlier, the boundary of a very large black hole is gentler than that of a smaller one. Tidal forces are weaker. Gradients are smoother. Matter approaching the horizon experiences less disruption at the boundary than intuition would suggest. This gentleness does not imply safety, but it does imply order. Crossing the event horizon of an object like TON 6118 would not involve sudden destruction at the boundary. The dramatic effects occur deeper inside, beyond observation. From the outside, the transition remains calm, governed by geometry rather than violence. This reinforces the idea that gravity, at its limit, is not about intensity, but about reach. TON 6118's reach is vast. Its influence extends far beyond what can be directly observed. Motion across large regions of its host galaxy is shaped by its presence. Time flows differently within its domain. Paths through space are subtly redirected, yet none of this requires action. Gravity does not act in bursts. It does not exert effort. It does not respond to attention. It simply exists as curvature, and everything else responds continuously. At extreme scales, this continuous response becomes the dominant narrative. There are no dramatic moments to point to. No single event defines the system. Its significance lies in persistence. In the fact that for billions of years, the same geometry has guided motion, shaped structure, and resisted change. This persistence invites a different kind of attention. Rather than watching for events, one must attend to patterns. Rather than expecting transformation, one must notice continuity. Understanding shifts from storytelling to observation of structure. This shift is necessary to grasp gravity at its limit. TON 6118 does not tell a story with a beginning and end. It presents a condition that has endured across cosmic time. Its gravity has shaped a region of the universe longer than Earth has existed. This realization reframes significance. The importance of TON 6118 is not that it is the largest known black hole, though that is true. Its importance is that it shows what gravity looks like when allowed to operate without interruption at the highest observed scale. It reveals a universe that favors stability over spectacle, persistence over drama, when time becomes part of the structure. As gravity deepens, time does not simply slow. It begins to lose its independence. In everyday experience, time feels universal. Seconds pass uniformly, regardless of location or motion. Even when we know intellectually that time can behave differently under certain conditions, that knowledge remains abstract. The effect is too small, too subtle to be felt. Time seems external, something that moves forward on its own. Near extreme mass, this assumption fails. In regions dominated by gravity like that of Ton 618, time becomes inseparable from space. It does not flow independently through the environment. It is shaped by curvature, stretched along with distances embedded into the structure of the region itself. This embedding changes how processes unfold. From a distant perspective, everything near an object like Ton 618 appears to move slowly. Signals take longer to arrive. Motion seems delayed. Change unfolds at a pace that feels almost static. This is not an illusion. It is a consequence of geometry. The deeper the curvature, the longer paths through space-time become. At extreme scale, time dilation is not a marginal effect. It becomes defining. Near Ton 618, time does not simply pass more slowly. It becomes unevenly distributed. Events closer to the center unfold on a different temporal scale than events farther away. The region develops a gradient of time, where duration itself depends on position within the curvature. This gradient reshapes causality. Cause and effect still operate, but their relationship stretches. Signals propagate more slowly outward. Feedback loops extend. Responses are delayed. The system becomes less reactive, not because it is inert, but because time itself resists compression. This resistance reinforces stability. Rapid change requires rapid time. Near Ton 618, rapid time does not exist. Processes unfold slowly by necessity. Instabilities that might grow quickly elsewhere are dampened. The system favors gradual adjustment over sudden transition. This is one reason extreme objects endure. Ton 618 is not frozen, but it is temporally insulated. Its internal dynamics are shielded from rapid external influence by the very geometry that defines it. Disturbances take a long time to propagate inward. Changes near the center take a long time to affect the outside. This insulation creates stillness. From far away, Ton 618 appears almost timeless. Its mass remains constant on observable timescales. Its influence does not fluctuate. Its environment settles into long-lived patterns. The object becomes a reference point rather than a participant in change. This timelessness is relative, not absolute. Locally, time continues. Motion continues. Processes occur. But the relationship between local time and distant time stretches so dramatically that the object seems detached from the flow of cosmic history. While the universe evolves around it, Ton 618 persists in a near-static state. This persistence reshapes perspective. In human narratives, time is often central. Events matter because they happen, because they change things. Near extreme mass, significance shifts away from events and toward conditions. What matters is not what happens next, but what continues to be true. Ton 618 exemplifies this shift. It is not defined by a sequence of actions, but by a state of being. Its gravity shapes a region of space-time that remains stable across immense durations. The universe can change around it without altering its fundamental role. This role is quiet, but profound. By reshaping time, Ton 618 alters the meaning of distance and duration simultaneously. Orbits stretch, periods lengthen, signals delay. The region becomes self-consistent in a way that resists interruption. This self-consistency is not imposed. It emerges naturally from scale. As mass increases, the curvature of space-time grows deeper and broader. Time stretches accordingly. The system becomes less responsive to short-term fluctuations. It favors equilibrium over change. This tendency is visible across the universe. Large structures evolve more slowly than small ones. Galaxies change more gradually than stars. Galaxy clusters change more gradually than galaxies. At each step upward in scale, time stretches. TON 618 sits at an extreme end of this progression. Its scale is so large that its characteristic timescales approach the age of the universe itself. This does not mean that nothing happens near TON 618. It means that what happens unfolds slowly, quietly, and without clear markers. Change becomes difficult to observe not because it is absent, but because it is distributed across immense spans of time. This distribution challenges observation. Astronomers observe TON 618 through snapshots separated by years or decades. Against the backdrop of billions of years, these intervals are negligible. The object appears unchanged. Its persistence is inferred rather than witnessed. This inference reinforces the impression of timelessness. TON 618 exists in a regime where the distinction between past, present, and future becomes less relevant. Events near the center are temporarily disconnected from distant observers. The usual synchronization of time breaks down. This breakdown is not disorder. It is structure. Time becomes layered. Different regions operate on different temporal scales. The universe accommodates this layering without conflict. There is no requirement that time flow uniformly everywhere. This realization deepens understanding of gravity at its limit. Gravity does not merely pull matter inward. It reorganizes reality. It shapes the stage on which events occur, including the timing of those events. At extreme scales, this reorganization becomes so thorough that time itself becomes part of the architecture. TON 618 is an architectural feature of space-time. It does not move through the universe in the way smaller objects do. It defines a region where the universe behaves differently. Within that region, motion, duration, and causality are reshaped into a stable configuration. This configuration persists. The endurance of TON 618 is not a mystery once gravity's role is understood. Given enough mass and enough time, such objects are not only possible, but inevitable. The universe allows them because its laws favor continuity over disruption. This continuity invites reflection. In a universe where time can stretch and slow, where objects can persist across cosmic history with little change, significance becomes relative. Importance is not assigned by size or activity, but by influence and endurance. TON 618's influence is immense, but quiet. Its endurance is vast, but unremarked. This combination makes it a powerful lens through which to consider the universe. It shows that the most extreme structures do not announce themselves. They do not demand attention. They exist steadily, shaping reality whether observed or not. This realization leads naturally to broader questions. What does it mean to exist in a universe where such objects are possible? How does human scale fit within a reality that accommodates mass and time on this level? How should meaning be understood when the universe operates so comfortably beyond intuition? These questions do not require immediate answers. They require space, time, scale, and meaning. When physics reaches its limits, questions change character. They stop asking what happens next and begin asking what it means that something can happen at all. Objects like TON 618 force this shift not through mystery, but through scale. They exist so far beyond ordinary experience that they cannot be absorbed into familiar narratives. Instead, they stand as reminders that meaning itself depends on perspective. Human meaning is local. It emerges from bodies that move at human speeds, live for human lifetimes, and occupy human-sized spaces. Our intuitions are shaped by what we can affect and what can affect us in return. Within that range, cause and effect feel immediate. Actions matter because consequences follow within visible time frames. Stories have beginnings, middles, and ends because our lives do. The universe does not share this constraint. At cosmic scales, time stretches until beginnings blur and endings dissolve. Objects persist for billions of years without significant change. Structures form slowly, remain stable, and fade only gradually. In this context, the idea of narrative loses traction. There is no urgency, no climax, no resolution. TON 618 exists entirely within this regime. Its presence is not a moment in history, but a condition that has endured across a significant fraction of cosmic time. It has no clear beginning that can be observed, and no foreseeable end that matters on human timescales. It does not participate in history as we understand it. It simply remains. This endurance challenges the way meaning is often assigned. In human terms, importance is frequently tied to activity. Things matter because they change something else. They intervene, they alter outcomes. At extreme scales, importance shifts from action to structure. What matters is not what happens, but what continues to be true. TON 618 matters not because it does something dramatic, but because it defines a region of reality. Its gravity shapes motion. Its mass shapes time. Its persistence shapes structure. These effects do not arrive as events. They are background conditions that everything else must navigate. This kind of significance is difficult to feel, but easy to overlook. When meaning is tied to immediacy, endurance appears passive. When meaning is tied to scale, endurance becomes dominant. The universe appears to value the latter. Its most influential features are not its most active ones, but its most stable. This preference for stability is visible everywhere. Atoms persist longer than chemical reactions. Stars persist longer than planetary climates. Galaxies persist longer than stars. At each level, larger structures change more slowly and shape the conditions under which smaller processes occur. TON 618 sits near the top of this hierarchy. Its scale ensures that it outlasts nearly everything around it. While galaxies evolve, merge, and fade, the black hole remains. While stars form and die, it persists. While cosmic expansion stretches space itself, its local influence remains coherent. This persistence invites a re-evaluation of scale-based meaning. If the universe's most enduring structures operate beyond narrative time, then meaning cannot be extracted from sequence alone. It must be inferred from pattern, from structure, from consistency across immense spans. TON 618 offers such a pattern. It shows that gravity, given enough time, produces stable, quiet outcomes rather than explosive ones. It suggests that extremes are not necessarily violent. They can be calm, ordered, and persistent. This contradicts many intuitive assumptions about power and scale. In human culture, power is often associated with action. Influence is measured by the ability to cause immediate change. At cosmic scales, power is associated with context. Influence is measured by the ability to shape possibilities over time. TON 618 shapes possibilities. It defines which paths are available, which motions are stable, which regions of space-time behave differently. It does this without acting, without changing, without responding. Its existence alone is sufficient. This sufficiency is unsettling in a quiet way. It suggests that much of reality operates independently of attention or intention. Structures exist because physical laws allow them to exist, not because they serve a purpose or convey a message. Meaning, in this sense, is not embedded in the universe. It is applied by observers. This does not make meaning illusory. It makes it relative. TON 6118 does not have meaning in itself. It acquires meaning when considered from a human perspective, when its scale is contrasted with human experience, when its endurance is compared to human lifetimes, when its calmness is set against expectations of drama. This comparison reveals limits. It reveals that human concepts of importance, urgency, and significance do not map cleanly onto cosmic reality. The universe is not arranged around what feels meaningful to us. It is arranged around what is stable. This realization can feel diminishing, but it does not have to be. Recognizing that meaning is local does not remove it. It contextualizes it. Human meaning remains valid within human scale. It matters that lives are short, that actions have consequences, that stories resolve. These features define experience, but they are not universal. TON 6118 reminds us that reality extends far beyond the conditions under which meaning evolved. It invites humility without demanding insignificance. It suggests that understanding does not require centrality. One can be small and still understand something large. Understanding in this context does not mean assimilation. It means acknowledgement. It means accepting that some structures will always exceed intuitive grasp, and that this excess is not a failure, but a feature. The universe is larger than understanding because it does not need to be understood to exist. This is perhaps the most important shift introduced by extreme objects. They reveal that comprehension is optional. Reality proceeds regardless. Structures form, persist, and fade without reference to observers. This independence is not hostile. It is neutral. TON 618 does not challenge humanity. It ignores humanity. This indifference is not a statement. It is a condition. In a universe governed by physical law rather than intention, meaning emerges where perception intersects structure. It is not discovered in objects themselves, but constructed in relation to them. This construction is not arbitrary. It is constrained by reality. Scale, time, and stability shape what can be meaningful. But within those constraints, interpretation varies. TON 618 allows one such interpretation. It can be seen as a limit case, a reminder of how far gravity can go. It can be seen as a marker of cosmic patience, a structure built not through violence, but through persistence. It can be seen as an example of how extremes need not be dramatic. None of these interpretations are imposed by the object. They arise from engagement. This distinction matters for how science and philosophy intersect. Science describes what exists and how it behaves. Philosophy considers what that existence implies for understanding, value, and perspective. TON 618 sits at the boundary between these domains. It is fully describable by physics, yet deeply resistant to intuitive meaning. This resistance creates space for reflection, not reflection in search of answers, but reflection in search of alignment. How should understanding adjust to accommodate scales that exceed narrative time? How should perspective shift when influence operates without action? These questions do not require resolution. They require acceptance. Acceptance that the universe contains structures far beyond human scale. Acceptance that meaning is not universal, but contextual. Acceptance that stability can be more powerful than change. TON 618 does not resolve these ideas, it illustrates them. It exists as a reminder that the universe is comfortable with extremes that feel unreasonable to intuition. It does not slow down to accommodate understanding. It does not simplify itself for observers. Yet understanding still progresses, through abstraction, through inference, through patience. In this way, TON 618 becomes a guide not to answers, but to posture. It suggests that when confronting scale, the appropriate response is not excitement or fear, but quiet attention. Significance without centrality. When confronted with something as large and enduring as TON 618, it is natural to ask where human significance fits. The question arises quietly, without urgency, as a byproduct of scale. If the universe can contain objects that persist for billions of years and shape regions of space larger than entire galaxies, what role is left for beings whose lives unfold across decades? This question assumes that significance requires centrality. Human history often places importance at the center of attention. What matters most is what happens here, now, to those who observe. Influence is measured by proximity. Meaning is often tied to impact. Within human societies, these assumptions work because scale is shared. Actions ripple outward within a common frame of reference. The universe does not operate within that frame. At cosmic scales, there is no center in the way human intuition expects. Space expands uniformly. No location is privileged. Objects do not matter because they are observed, but because they are stable within the laws that govern everything else. TON 618 is not significant because it is noticed. It is significant because it persists. This persistence does not erase smaller scales. It contextualizes them. Human significance does not diminish simply because larger structures exist. It changes character. Meaning becomes local rather than absolute. Importance becomes relational rather than universal. What matters is not how one compares to the largest objects, but how one fits within the scale one inhabits. TON 618 does not compete with human experience. It exists alongside it on a different axis. This coexistence reveals something subtle. The universe allows many layers of significance to exist simultaneously. Atomic interactions matter at atomic scales. Biological processes matter at biological scales. Cultural meaning matters within societies. Cosmic structures matter at cosmic scales. None of these invalidate the others. The mistake arises when significance is treated as hierarchical rather than contextual. When larger is assumed to be more meaningful simply because it is larger. The universe does not appear to support this assumption. It supports coexistence. TON 618 does not overshadow human meaning. It ignores it. This indifference is not dismissive. It is neutral. The universe does not rank importance. It allows structures to persist where conditions permit. Meaning is not assigned by size, but by relevance within a given scale. From this perspective, human significance remains intact. Human understanding, creativity, and reflection operate within a narrow window of scale. But within that window, they are profound. The fact that the universe extends far beyond that window does not negate what occurs inside it. It simply places it within a larger context. TON 618 helps clarify this distinction. It demonstrates that extremes exist without intention. They are not messages. They are not judgments. They are outcomes of physical law operating consistently across time. Their existence does not imply that smaller scales are less valid. It implies that reality accommodates diversity of scale. This accommodation is generous. The universe does not compress itself into a single frame of relevance. It allows different processes to unfold at different rates, across different distances, without requiring alignment. Time flows differently in different regions. Motion follows different patterns. Stability takes different forms. Meaning emerges where awareness intersects these patterns. Human awareness is limited, but that limitation does not disqualify it. It defines it. Meaning arises precisely because perspective is bounded. Without limits, significance would dissolve into uniformity. Ton 6118 is significant because it sits at an extreme. Human life is significant because it sits within a narrow band where perception, memory, and intention overlap. These forms of significance do not compete. They occupy different domains. This realization softens the impact of scale. Instead of diminishing experience, it enriches it. Knowing that the universe contains structures far beyond human scale does not make human concerns trivial. It makes them specific. It gives them context without removing their weight. Ton 618 does not ask to be admired. It asks to be understood within its domain. Human meaning does the same. This parallel is subtle, but important. Both exist because conditions allow them to exist. Both persist as long as stability remains. Both are shaped by laws that operate without regard for narrative or intention. The difference lies in awareness. Ton 618 does not reflect on its existence. Humans do. This reflection is not a flaw. It is a feature of a particular scale of complexity. It allows meaning to be constructed rather than inherited. In this sense, understanding extreme objects like Ton 6118 becomes an exercise in alignment rather than comparison. It asks not how we measure up, but how perspective shifts when scale changes. Alignment requires humility, but not erasure. It requires acknowledging that human understanding is partial, while accepting that partial understanding is still understanding. It requires letting go of the need for centrality while retaining the value of context. Ton 618 invites this posture. It stands as a reminder that the universe is not arranged around observers, yet remains accessible to observation. It does not yield meaning automatically, yet supports the conditions under which meaning can arise. This balance is quiet. There is no conflict between cosmic scale and human relevance. There is only difference. The universe contains more than one way for things to matter. This insight becomes clearer when considering time. Human time is brief, but dense. A great deal happens within a small span. Relationships form, knowledge accumulates, stories unfold. Cosmic time is vast, but sparse. Change is slow. Structures persist. Events are rare. Neither form of time is superior. They are suited to different kinds of existence. Ton 618 belongs to a form of time where endurance is the primary feature. Humans belong to a form of time where change is central. Meaning arises differently in each, but arises nonetheless. This distinction helps dissolve a common misconception. Scale does not determine value. Context does. Ton 618 is valuable to understanding because it reveals the outer limits of gravitational structure. Human experience is valuable because it reveals what awareness looks like within finite bounds. Both contribute to a fuller picture of reality. Neither needs to dominate the other. This realization allows reflection to settle. There is no need to resolve the tension between small and large, brief and enduring, active and still. The universe accommodates all of these simultaneously. It does not ask for reconciliation. It allows coexistence. TON 618 exemplifies coexistence without interaction. It exists far away, unaffected by human observation, yet it can still be known, modeled, and contemplated. This asymmetry does not diminish the act of understanding. It underscores its one-sided nature. Understanding is something humans do. The universe does not reciprocate. This lack of reciprocity is not emptiness. It is openness. It allows meaning to be constructed freely, constrained only by reality rather than intention. It allows reflection to unfold without expectation of response. TON 618 does not answer questions. It reframes them. It shifts focus away from dominance and toward endurance, away from action and toward structure, away from narrative and toward context. In doing so, it offers a quieter kind of insight. Not insight that resolves uncertainty, but insight that makes uncertainty livable. Insight that replaces urgency with patience. Insight that allows scale to exist without requiring assimilation. This is perhaps the deepest contribution of extreme objects. They do not expand understanding by adding detail. They expand it by revealing limits and showing that those limits are not barriers, but boundaries that shape perspective. TON 618 sits at one such boundary. It marks the edge of intuitive scale, the region where comparison dissolves and meaning becomes contextual. It does not need to be crossed. It only needs to be acknowledged. With this acknowledgement, the narrative begins to settle. The quiet that remains. When attention moves away from extremes, nothing disappears. The universe does not reset. It continues. Objects like TON 6118 do not linger in awareness because they demand it. They linger because once noticed, they subtly alter perspective. After considering scale that exceeds intuition, the familiar world does not shrink, but it feels differently framed. Distances feel more conditional. Time feels less absolute. Stillness feels more substantial. What remains is not astonishment, but quiet. TON 618 does not conclude a story. It does not resolve a question. It does not sit at the end of a sequence of ideas. Instead, it settles into the background, where the most influential structures tend to reside. Its role is not to be watched, but to persist. This persistence is easy to overlook. Human attention is drawn to change. We notice what begins and what ends. We track motion, contrast, interruption. What remains constant recedes from focus, even when it shapes everything else. Gravity itself is often unnoticed until it is absent. Time is rarely questioned until it behaves unexpectedly. TON 618 belongs to this category of unnoticed foundations. Once the scale is acknowledged, the object does not require continued emphasis. It does not benefit from repetition. Its significance lies not in continued description, but in quiet acceptance. It exists. It persists. It shapes a region of the universe without needing to announce itself. This quality aligns it with much of reality. The deepest features of the universe are not its most visible ones. Dark matter does not shine. Space-time does not glow. The largest structures are traced indirectly through motion and pattern, rather than appearance. Their presence is inferred because it must be, not because it wants to be seen. TON 6118 fits this pattern. Its influence is evident in the motion of matter around it, in the light emitted far from its boundary, in the stability of its environment. The object itself remains dark, silent, unchanged. It does not compete for attention with the processes it enables. This restraint is instructive. In a universe that allows extremes, significance is not always loud. It is often cumulative. The most important features are those that endure without interruption, allowing other processes to unfold around them. TON 618 allows galaxies to organize. It allows motion to settle. It allows time to stretch. It does this by remaining what it is. There is no requirement that such an object be understood fully. Partial understanding is sufficient. Knowing that it exists, knowing roughly how massive it is, knowing how it behaves, these pieces form a complete picture in context. Precision, beyond that, does not change the nature of its role. This is an important distinction. Human knowledge often aims for completeness, but the universe does not demand it. Understanding is not a prerequisite for existence. Structures form, persist, and fade regardless of whether they are measured precisely. What matters is that they are consistent. TON 618 is consistent. Across different methods of observation, across different models, across different assumptions, it remains extreme. The details vary. The central fact does not. This consistency allows the object to recede into the background of understanding without losing relevance. When something can be relied upon to persist, it becomes part of the setting rather than the subject. This shift mirrors how humans relate to their own environments. Mountains become background. Oceans become background. The sky becomes background. Their influence remains profound, but their presence becomes assumed. They are no longer events. They are conditions. TON 618, once acknowledged, becomes a condition of cosmic structure. This does not diminish its importance. It clarifies it. By becoming background, the object stops demanding interpretation and begins offering orientation. It helps define the range of what is possible. It marks a boundary not of law, but of scale. It shows where gravity, time, and endurance can reach without breaking. This boundary does not close understanding. It stabilizes it. There is comfort in knowing that the universe is capable of such stability, that it can host objects of immense mass without collapsing into chaos, that extremes do not necessarily imply fragility. TON 618 suggests a universe that favors order at large scales. This order is not imposed. It emerges. It emerges from laws that do not change with scale, from gravity that behaves the same whether shaping planets or defining regions larger than galaxies, from time that stretches smoothly rather than breaking abruptly. The quiet of TON 618 is a consequence of this smoothness. Nothing about the object requires urgency. There is no impending transformation that must be anticipated, no threshold that will be crossed suddenly. Whatever changes occur will unfold slowly, on timescales that dwarf observation. This slowness has an effect on perspective. When confronted with processes that operate beyond urgency, attention relaxes. The need to track outcomes diminishes. Curiosity shifts from prediction to acceptance. One stops asking what will happen next and begins noticing what continues to be true. TON 618 continues to be massive. It continues to shape space-time. It continues to persist. These statements do not form a narrative. They form a condition. This condition does not exclude change elsewhere. The universe remains dynamic. Stars form and die. Galaxies merge. Expansion continues. Within the context shaped by TON 618, these processes unfold according to the geometry that exists. The object does not resist change. It contextualizes it. This contextualization is subtle. It does not direct events. It does not orchestrate outcomes. It defines possibilities. It determines which paths are available, which motions are stable, which timescales dominate. In this way, TON 618 functions less like an actor and more like terrain. Terrain is rarely the focus of stories, yet it shapes every journey. It determines routes, durations, and outcomes without ever moving itself. Its influence is constant, but understated. This analogy, though imperfect, captures the role of extreme mass. TON 618 is not something that happens. It is something that everything else happens within. Recognizing this allows attention to move on without loss. The object does not need to be held in mind continuously to matter. Its influence persists whether noticed or not. This persistence aligns with a broader theme. The universe is not structured around observation. It does not prioritize awareness. It allows structures to exist independently of attention. Understanding is something added later, by observers after the fact. This asymmetry is fundamental. TON 618 does not change when observed. It does not respond. It does not acknowledge. It remains indifferent to inquiry. This indifference is not hostile, it is neutral. In neutrality, there is room for interpretation without obligation. Humans can assign meaning, draw insight, reflect on scale. The object does not resist these interpretations, but it does not require them. Its existence is complete without commentary. This completeness is rare in human experience, where meaning is often bound to interaction and response. TON 618 exists without feedback. It does not participate in dialogue. Yet dialogue still occurs among observers. Through discussion, modeling, and reflection, understanding evolves. Not because the object changes, but because perspective does. Each generation of observers approaches the same structure with different tools, different assumptions, different questions. The object remains. Understanding moves around it. This dynamic, fixed structure, evolving interpretation, is characteristic of deep reality. Laws remain stable, contexts shift, meaning adapts. TON 618 fits comfortably within this pattern. It does not demand reinterpretation, it accommodates it. As attention recedes further, the object becomes part of a larger backdrop of extreme but stable structures. It joins galaxy clusters, cosmic filaments, and the expansion of space itself as features that define the universe without narrating it. These features do not tell stories. They allow stories to occur. This allowance is easy to miss because it is constant, but it is foundational. Without stable structure, nothing else could unfold coherently. Without persistent conditions, change would be meaningless. TON 618 contributes to this stability, not locally in a way that affects human experience directly, but cosmically, as part of the architecture that allows complexity to exist elsewhere. Its role is distributed across space and time, not concentrated at a point of action. This distributed influence is difficult to appreciate, but once noticed, it reframes understanding of what it means for something to matter. Importance does not require proximity. Significance does not require activity. Sometimes what matters most is what remains unchanged while everything else adjusts. This idea does not resolve into a conclusion. It settles into awareness. TON 618 fades from focus not because it is exhausted as a topic, but because its role is complete once acknowledged. It does not benefit from repetition. It does not deepen with emphasis. Its meaning lies in presence, not elaboration. This fading is appropriate. The object belongs to the background of cosmic structure, where the most enduring features reside. Bringing it forward repeatedly would distort its nature. Letting it recede honors its role. What remains, then, is not the object itself, but the perspective it leaves behind. A sense of scale that is less urgent, a sense of time that is less rigid, a sense of meaning that is less centralized. These shifts do not demand attention. They persist quietly. The quiet giant remains. In the end, nothing concludes. There is no final image that captures TON 6118, no moment where its meaning resolves into something definitive. The object does not move toward an ending, because it was never moving toward a beginning. It exists in a state that is largely independent of sequence, a condition rather than a story. This is what remains when attention settles. TON 6118 continues to exist far beyond human reach, unchanged by observation, unaffected by interpretation. It does not grow rapidly, it does not diminish, it does not react. Its gravity continues to shape a region of space-time in the same way it has for billions of years, and likely will for billions more. This continuity is not dramatic, it is complete. The universe does not mark the presence of such an object with emphasis. There is no signal that says this is the largest, or the most extreme, or the most important. There is only structure behaving as structure does, governed by laws that apply everywhere and always. TON 6118 is one expression of those laws. It is not separate from the universe. It is not an exception. It is gravity operating at a scale that exceeds familiarity, but not consistency. The same principles that guide a falling stone guide the motion of matter near this black hole. The difference lies only in reach and duration. This sameness across scale is easy to overlook. Human attention gravitates toward difference. We notice what stands out, what violates expectation, what demands adjustment. TON 6118 stands out numerically, but not behaviorally. It does not violate expectation in how it behaves. It follows the rules precisely. Its extremity is one of quantity, not quality. This distinction matters because it reframes how extremes are understood. They are not warnings, they are confirmations. They show that laws hold even when pushed far beyond the conditions under which intuition evolved. TON 6118 confirms that gravity remains gravity, even when mass becomes immense. That time remains time, even when stretched. That stability remains possible, even when scale becomes overwhelming. In this confirmation, there is a quiet reassurance. The universe does not become unpredictable at its edges. It becomes more abstract, but not less ordered. Understanding becomes harder, but reality does not become chaotic. The difficulty lies in perception, not in structure. TON 6118 highlights this gap. It exists comfortably in a regime where human imagination struggles, but physical law remains at ease. The universe does not hesitate when producing such an object. It does not require special conditions beyond persistence and opportunity. It simply allows gravity to continue. This allowance produces endurance. Endurance at this scale is not resistance to change. It is indifference to it. Changes elsewhere do not significantly affect the object. Local fluctuations are absorbed into the broader geometry. The system remains stable because it is large enough to make disturbance insignificant. This quality is rare in human experience. Human systems are sensitive. Small changes can have large effects. Structures are often fragile. Meaning is often contingent. TON 618 exists in a regime where fragility gives way to inevitability, where influence is distributed so broadly that disruption becomes unlikely. This inevitability is not destiny. It is geometry. Space-time curve this deeply does not permit rapid rearrangement. It favors continuation. It smooths sharp differences. It stretches responses until urgency dissolves. In this sense, TON 618 is not active. It is settled. The word settled is important. It implies completion without finality, a state reached through accumulation rather than arrival. A configuration that does not seek further change, yet remains open to it if conditions allow. TON 618 does not seek growth. It does not seek rest. It simply exists in balance. This balance is not static in the strict sense. Processes still occur, matter still moves, time still flows locally, but these processes unfold within a framework that is so dominant, so encompassing, that their effects do not alter the whole. This is what it means to remain. Remaining is not passive, it is structural. The universe contains many structures that remain. The laws of physics, the expansion of space, the large-scale distribution of galaxies. TON 618 joins this category, not because it is fundamental, but because it is persistent. Its persistence is a product of scale, not privilege. This understanding allows the object to recede fully into context. It no longer needs to be foregrounded. It does not demand explanation beyond what has already been given. Its role is established. What remains then is perspective. After encountering an object like TON 618, the universe does not look the same, even though nothing has changed. Scale feels less personal. Time feels less urgent. The expectation that significance must be tied to action weakens. These shifts are subtle. They do not announce themselves. They do not alter daily experience directly. But they linger, adjusting how questions are framed and how answers are weighted. This lingering is the true impact of extreme scale. TON 618 does not leave behind facts to memorize. It leaves behind a posture of understanding, one that is slower, less insistent, more tolerant of abstraction. A posture that accepts that some things will always remain larger than imagination, and that this is not a problem to be solved. The universe does not ask to be reduced. It asks to be approached carefully. TON 618 encourages this care. It demonstrates that the most extreme objects do not demand urgency. They reward patience. They do not yield meaning through excitement. They invite reflection through endurance. This invitation does not require acceptance. It exists regardless. One may acknowledge TON 618 and move on. One may forget its name. One may never encounter it again. The object will remain unaffected. Its gravity will continue shaping its region. Its time will continue stretching. Its presence will continue to define context. Understanding does not alter reality. It aligns perspective with it. This alignment is quiet. It does not culminate in insight that can be summarized. It settles into a background awareness that scale is vast, that time is flexible, and that stability can exist without spectacle. These are not conclusions. They are conditions. The universe contains many such conditions, operating continuously without attention. TON 618 is one of them. It does not need to be exceptional to matter. It matters because it exists within the same framework as everything else. This sameness is perhaps the most grounding realization. No matter how extreme an object becomes, it remains governed by the same principles. There is no point where reality breaks into something alien. There is only a gradual shift away from intuition. TON 618 sits far along that shift. It does not represent an end. It represents a continuation of gravity shaping structure. a continuation of time stretching with mass, a continuation of the universe producing forms that endure. This continuation does not resolve. It persists. As attention finally releases its focus, the object fades into the larger background of cosmic structure where it belongs. It does not disappear. It simply stops being centered. And in that decentering, the universe feels larger, calmer, and less urgent. The quiet giant remains, letting the scale drift away. Eventually, attention loosens its grip. Not because there is nothing more to say, but because nothing more needs to be held. The object remains where it has always been, far beyond reach, beyond immediacy, beyond the rhythms that define everyday experience. What changes is not Tan 618, but the way it occupies thought. It drifts outward, away from focus, back into the quiet architecture of the universe. This drifting is natural. The mind is not meant to hold extremes indefinitely. It approaches them, learns their contours, adjusts its sense of scale, and then releases them. What remains is not detail, but orientation, a subtle recalibration of how vastness is understood. Tan 618 does not need to stay vivid to matter. Its role is complete once perspective has shifted. Once it is clear that such objects can exist calmly, persistently, without disruption. Once it is understood that gravity, time, and structure do not grow unstable at the edges of scale, but instead become smoother, slower, and more settled. This understanding does not demand remembrance. It simply integrates. The universe continues to unfold in the same way it always has. Space expands. Galaxies move. Stars form and fade. Somewhere far beyond observation, Tan 618 remains, shaping a region of space-time that will likely never intersect with human history in any direct way. This separation is not loss. It is clarity. Not everything that matters must be close. Not everything that exists must participate in shared experience. Reality is layered, with processes unfolding independently across scales that rarely intersect. Tan 618 belongs to a layer defined by endurance. Human lives belong to layers defined by change. These layers coexist without conflict. One does not invalidate the other. They simply operate under different conditions, guided by the same underlying laws. This shared foundation is easy to miss. At first glance, the universe appears fragmented. Particles here, planets there, galaxies farther still. But beneath this apparent fragmentation lies continuity. The same principles operate everywhere, shaping outcomes according to context and scale. Tan 618 is not alien. It is familiar laws applied patiently. This patience is perhaps the most striking lesson left behind. Nothing about Tan 618 required urgency. Its formation did not demand haste. Its existence does not require maintenance. Its future does not hinge on intervention. It persists because the universe allows persistence where stability is possible. This allowance is quiet. It does not announce itself. It does not impose meaning. It simply exists as a background condition that makes other processes possible. Without stable structures at large scales, smaller complexities could not emerge. Tan 618 contributes to this stability indirectly, not by acting, but by remaining. By defining a region where motion is ordered, where time stretches, where disturbance fades into insignificance. This role is not dramatic, but it is foundational. As attention continues to recede, even this role becomes abstract. The object no longer appears as a subject of thought, but as part of the universe's deeper texture. Like space itself or time itself, it becomes something that is not actively contemplated, yet quietly assumed. This is where the documentary truly ends, not with a conclusion, but with a return to background. The extreme dissolves into the ordinary structure of reality. The extraordinary becomes part of what simply is. TON 6118 remains. It remains whether remembered or forgotten, named or unnamed, studied or ignored. Its existence does not depend on awareness. Its significance does not require recognition. This independence is not cold, it is neutral. The universe does not reward attention or punish neglect. It allows understanding, but does not require it. Structures persist because they are stable, not because they are meaningful. Meaning arises elsewhere. It arises in the act of noticing, in the effort to understand, in the willingness to let understanding remain incomplete. It arises when scale is acknowledged without being reduced, when vastness is accepted without being dramatized. This acceptance is quiet. It does not rush. It does not conclude. It simply allows thought to settle, the way matter settles into orbit, the way systems settle into equilibrium. TON 6118 no longer needs to be foregrounded. It has done its work. What remains is a slightly altered sense of time, a softened sense of scale, and a deeper tolerance for the fact that reality extends far beyond intuition without becoming chaotic. The universe continues. Somewhere far beyond light that will ever reach this moment, gravity continues to curve space-time smoothly. Time continues to stretch and layer itself. Stability continues to outlast change. The quiet giant remains, not as a spectacle, but as part of the enduring background against which everything else unfolds. And with that, attention is free to drift. No ending is required.